Today's lecture is about detection transformer. There are two things that I have planned for today. One is understanding the full intuition about detection transformer. And then today we will not be writing detection transformer from scratch, but rather we will be implementing detection transformer for inference. That will be much easier to do. The only difficulty with detection transformer implementation from scratch is not with respect to coding part, it's with respect to accuracy. So it requires long duration of training to get good accuracy. So far in my implementation, the accuracy is very, I would say, pathetic compared to any other previous architectures we have implemented as part of this course. So if the accuracy is really good, I do plan to, if I manage to get good accuracy on any simple data set, like COCO or any other VOC or any data set, I will conduct one lecture on implementation. Otherwise, we'll see. I'll figure out what to do, whether a full from scratch implementation is worth it or not. I'm yet to decide. But in any case, from today's lecture, you will understand detection transformer entirely. And I really want you to pay good attention today because there are some aspects of detection transformer that are easy, but the volume of things that you have to keep in your mind at the same time is a little bit too much. I'm not saying that detection transformer is difficult to understand. Swing was difficult to understand, but detection transformer is easy to understand. It's just that you have to just pay attention to multiple parts at the same time. There is a question whether VLMs are state of the art now. I mean, VLM is a broader term. There are many. VLM is just a term that is used to signify that you want to bring alignment between text and vision. That's all. So state of the art, it depends on the context, right? In the context of detection or in the context of vision and language alignment, or in the context of classification, there are different models that are state of the art. Yeah, I agree. Like implementing from scratch is still worth it, even if accuracy is bad. Yes, I completely agree. So at least I need some respectable accuracy to feel good about it. But let's see. So first of all, what is object detection? Object detection, you might have seen models like YOLO. They are famous models. We'll implement object detection using detection transformer today, but the end goal is to get bounding boxes like this. So these bounding boxes will localize the object. In classification, remember, the whole image is classified. The whole image is set to be label A or B or whatever. In detection, we say locally inside this bounding rectangle, there is a person, the class is person, with 64% confidence. Inside this light blue rectangle, there is a dog with 30% confidence and horse with 28% confidence. So here, if you see within one image, you are producing sort of multiple predictions. If this was a classification problem, it would have been, I mean, there are multi-level classification problems, of course, but generally it is conducted for the whole image, not for some localized part of the image. So there are three things we should know. One is we do localization. What do we mean by that? We are able to pinpoint and say that the object of interest is within this rectangle inside the image. We can perform classification. What do I mean by that? Inside this rectangle. So if you now consider that this rectangle is another image, that image now can be classified. We can classify whatever is that in that rectangle to be horse or cat or person or whatever, right? So some type of classification we have to perform. We also have to display some sort of confidence score like this 0.28, 0.3, whatever. So usually object detection models, these are some famous object detection models. Before detection transformer, there were object detection models that purely relied on convolutional neural network. There was no transformer architecture. Some of the models are called YOLO. YOLO is called you only look once. YOLO is the state of the art for real-time fast object detection. Then there are other models like Fast R-CNN, Faster R-CNN, Mask R-CNN for drawing mask. So there are many different models for object detection. There is real-time detection transformer, RT-DETR. So there are many models for object detection, out of which the models which use transformer in its architecture are like DETR and other variants. So in the whole architecture, the idea is very simple. You have an input image, and the model will try to predict a bounding box. Now, bounding box can be defined using few things, right? Let's say you are given the coordinates of the centroid of this rectangle, and you are given the height and width. You just need how many numbers to represent this rectangle, how many numbers are sufficient for you to draw a rectangle at an exact location in the image. Can you just mention in the chat? 3 or 4. You will need 4 numbers, right? X coordinate of the center, Y coordinate of the center, height of the rectangle, width of the rectangle. So if you have 4 numbers, you can uniquely determine a rectangle. In addition to that, you need what is the class. So whether the class inside that rectangle, whether it's a dog or cat or whatever, what is the confidence score? So all in all, let's say you need sort of like 6 items, right? Class, label, confidence score, width, height, center coordinates in X and Y. Now, if we were to build a naive object detection algorithm without considering YOLO or transformer or anything, just look at what are the input output pairs. Input is in classification, input is an image, output is what? In classification, what is the format of the output? Let's say it's a binary classification. What does it look like? The output look like mathematically? It's not yes or no, right? It's not binary. It's never binary. I mean, classification is supposed to be binary, but you have sort of like a vector with 2 entries, right? You will never have 100% confidence that something is a dog. You will have 99.999%. So your output will be like a vector. In this case, it will be like 0.92 for dog and 0.08 for cat. In this case, it will be 0.15% for cat and 85% for 0.15 for dog, 0.85 for cat. This is label 0. This is label, label number ID1, label ID0, label ID1. So here you say that because the output probability distribution is leaning towards class 0, the object is, or whatever is inside, whatever this image is of class 0. And in this case, this is leaning towards class 1 and class 1 is cat. This is the case if you are performing classification. So essentially think about it. You have some neural network, ignore whether it's a convolutional neural network or whatever. You have some neural network which takes image is bunch of pixels. It takes image as an input and outputs something like a vector, right? At the end of the day. Now, by the same logic, can you think of, so this was about classification problem. So this output is for classification, not for detection. By the same logic, if we were working on detection problem, what could the output vector look like? Oh, one more question before that. Now, this is the prediction, right? This is y cap. And we compare this against something to produce the loss, right? We compare this against ground truth. What does the ground truth look like? Ground truth will look like, in this case, 1, 0. Similarly, this is the y cap prediction for the this image. The ground truth will look like 0, 1 in this case, right? So you compare y cap with y using cross entropy loss. So you can simply say minus yi log pi, where pi is the prediction, yi is the actual label, and sigma I equal to 1 to 2. So here the loss will look like, in this particular case, it will look like minus log E 0.92. In this case, the cross entropy loss will look like minus log 0.85. Because the other term will, although it's a sigma over I equal to 1 to 2, the other term will cancel because it will be 0 multiplied by log of 0.15 plus 1 multiplied by log of 0.85, everything with a negative term, with a negative sign. So this is the loss which we define in classification problem. Now let's forget about classification problem. If we wanted to do something very similar for detection, object detection, let me erase all of this. Just tell me, what should my output look like, or what will my ground truth look like? So let's say this is my input image. What might the ground truth look like? The ground truth, first of all, it will have, let's say, 6 terms, right? we discussed there are 6 terms. One is class. So if dog is of class 0, or rather class 0, yeah. So dog is class 0. The confidence with which this is a dog is 1 for ground truth. We need x, y, width and height. So everything will be normalized between 0 and 1. So let's say the x coordinate and y coordinate of the center is in normalized coordinates is 0 0.5, comma 0 0.5. And let's say height is also like around 60% of the height of the image. So let's say height and width are like 0.65, 0.65, something like this. So now this is y equal to this. This is the ground truth. So this denotes class. So class 0. This denotes probability 1, because this is ground truth. 0.5 is the normalized x coordinate of the center. 0.5 is the normalized y coordinate of the center. 0.65 is the normalized height of the bounding box with respect to the height of the image. 0.65 is again the height of the width of the bounding box with respect to the width of the image. Now the prediction made by neural network, it need not be convolutional neural network. It can be whatever it is. It has to look something like this. It may look like y cap equal to, it will it will not say, okay, by the way, I missed one more term. Maybe I should have 0, 1, 0. Okay, I think this is fine. So this may say something like 0. I should have a probability distribution. So let's add actually 2 terms. So if this is a dog, I will have 0, 1, 0 is the class for dog. So my prediction might look like 0.9 to 0.08. Confidence might be 0.7. Bounding box center coordinates might look like 0.45, 0.3. Height of the bounding box may look like 0.5 and 0.62, whatever. So basically, if my ground truth rectangle is something like this, my actual predicted bounding box will be slightly different. And then same, we can construct loss between these two. There are many different types of losses. The simplest loss you can think of is element-wise subtraction. Take absolute value, add them up. Or element-wise subtraction, take a square, add them up, right? So we can think of many different types of loss functions to construct if we wanted to build a very naive object detection model. But of course, this has a lot of limitations, because here this can only detect one object in the image. What if my image had 2 dogs? Like the example image which I showed here, there were 3 objects in this image. So then my dimension, right now this has what? 1, 2, 3, 4, 5, 6, 7 dimensions. It's like 7 by 1. But what if I had 2 objects, 2 different type of objects? What if I had multiple objects of the same class? Then there are many such issues that this vanilla or naive object detection model algorithm cannot take care of. But that is okay, because here the point is just to make you understand or make you think about, okay, what may this object detection model look like if you were to build something completely from scratch without transformer, without anything, right? You will simply have an input image. You will have some sort of neural network with or without convolution. With convolution means, of course, you will have better feature extraction. And then output, you will get one vector. That vector you will compare with your ground truth. Okay, so now this is the basic of how, if you were to build an object detection model for the first time in the history of computer vision, this is maybe what you may try in the very beginning. But people have already tried it. There are other good models like YOLO, which does take care of some of the problems which I mentioned. If there are small objects inside the image, if there are multiple objects inside the image, how those things are taken care of. I have conducted detailed lectures on this as part of one of the courses earlier. So if you are interested in that, check that out. But in any case, we are going to discuss detection transformer right now. So detection transformer, again, as name suggests, it's for object detection with the help of transformers. Now you may wonder, does it mean that there is no convolution operation involved? There is actually convolution operation also involved, but transformer plays a huge role. In fact, there are two types of transformer here: transformer encoder and transformer decoder. We will see all of that. The paper is from Facebook AI in 2020. It has 21K citations. So it's like a highly cited paper. You will still see detection transformer models being used for inference. So the paper makes some claims meaning why the paper is better than some of the earlier techniques that existed. So some of the earlier techniques depended on something called as anchor boxes. I will define what anchor boxes is. Even if you don't fully understand what exactly are anchor boxes, it will not affect your understanding of today's lecture. But I'm just saying, in case you plan to read the paper, when you read about anchor boxes in the paper, I just want you to visualize something. I will show you what that is. So this detection transformer eliminates the need for anchor boxes. It also eliminates the need for something called as non-maximum suppression. So maybe you should also understand what is non-maximum suppression. Even if you don't understand, you will fully understand detection transformer. But when you read the paper, you may wonder what is non-maximum suppression. So let's discuss briefly about these two things, and then we will look at the architecture. So some models, like later models of RCNN, Faster R-CNN, for example, what they did was, instead of directly predicting a bounding rectangle out of the blue, instead of directly saying, hey, here is my bounding rectangle, what they did was they predefined bunch of anchor points. So here you can see these crosses. These are all anchor points aligned like a nice grid. And around these anchor points, they defined 9 anchor boxes. So these yellow boxes are actually 9 boxes overlapped on top of each other. And these boxes came in different sizes and different aspect ratios. Some boxes are more like square. For example, like this is more like a square one, but this one, for example, has a lean aspect ratio. This one has a lean aspect ratio. So the reason why anchor boxes were defined was because what you can do if you start with anchor boxes is you can simply modify the size and position of the anchor box little bit. So you try to modify the height of this anchor box by 10% and width by 5% and center coordinates by 2% in certain direction, and see whether the anchor box is moving closer and closer towards your ground truth in the training. And you do that for all anchor boxes for all the anchors. So essentially what happens is you will be able to make predictions for objects with weird aspect ratios. So weird aspect ratio meaning, see, this is a phone. And this one, if I'm holding it like this, it has a certain aspect ratio. But then if I'm holding it like this, it's the same object, but now the aspect ratio has completely changed. So earlier object detection models has had issues with extremely high values of aspect ratios or extremely low values of aspect ratios, because and that may happen in reality. Aspect ratio fully depends on from which angle you are looking at the object. So if the same camel, if you are looking at from the front or back, it will look like lean, its aspect ratio will be higher. So what they did was, by defining these anchor points, which are starting points, and by defining these anchor boxes as starting boxes, and by modifying those boxes little by little by little during the training, you can come up with good predictions, good bounding box predictions, which are closer and closer to the ground truth. So this was one idea. For the purpose of today's lecture, you don't have to understand how exactly the modification is done. I will simply say modification was done using some sort of regression. So you regress the height, width, center coordinates little by little to make the box better and better. Does it mean that it can detect 9 objects only for 9 anchor boxes? So the entire image will not have only 9 anchor boxes. It will have 9 multiplied by how many of our anchor points are there. So these anchor boxes are all centered around this point. So this grid is like a very nice grid. So grid is predefined. Anchor boxes are also starting points of anchor boxes are also predefined. So total number of anchor boxes in the starting will be 9 multiplied by whatever is the number of grid points. So you will start from that as the starting point, and then you will try to modify the shape and position of anchor boxes and try to see which anchor boxes are correlating the best with ground truth. So this is what is done in the training, but I'll come to some problems with that. So this was a complex algorithm, of course, but all I want to take away from this is previous algorithms relied a lot on hand engineered anchor boxes. Already you have asked question, how many anchor boxes? It's decided by human. What should be the aspect ratio of these anchor boxes? Again, decided by human. So these are all hand engineered aspects of the previous algorithms before detection transformer. One more thing which I want to mention is, so anchor boxes detection transformer managed to eliminate. That is one point. Just keep it in your mind. This will not affect your understanding of detection transformer. Second thing is, it also eliminated the need for something called as non-maximum suppression. Now, this part is kind of easy to understand. So non-maximum suppression simply means, let me skip this and I'll just draw and show you something. Let's say you are running a detection transformer algorithm during inference, okay? Now, if you are using a model which has anchor boxes, what will happen is you will make predictions. You will make boxes that are predictions. And let's say you have one box like this and another box that looks like this. Then you have another set of two boxes that look like this. Okay. So this is your whole prediction. Now, this is my image. My image is this big rectangle. Let me just fill something. Okay. So think about this. If I have an image and if I have 4 boxes in the final prediction, what should I conclude from this? Should I conclude that there are 4 objects in this image? Is that the conclusion that I should come up with by looking at the fact that there are 4 predicted boxes? Not necessarily. The reason is maybe there are multiple anchor boxes that evolved to predict objects like that are duplicates. Duplicates as in this box is predicting object A. This is also predicting object A. This box is predicting object B. This is also predicting object B. Now, how do you know that? Because in inference, you don't know how many objects are there. You are just passing an image. There is no ground truth available to you, right? You simply have a bunch of anchor boxes and you have ground truth. You don't have ground truth. Now you have to tell how many objects are there and which are the anchor boxes that correspond to your object. So to do this is why people introduced the algorithm called non-maximum suppression. So let's go through the algorithm steps one by one, and then we'll come back to this and you will understand what is the algorithm. So non-maximum suppression starts like this. So firstly, we don't just predict bounding boxes. We also predict boxes with confidence score, right? So this box may have a confidence score of 0.9. Maybe this has confidence score of 0.3. Maybe this is predicted with 0.85. This is with 0.7. So boxes are associated with confidence score. So first thing is you sort the boxes based on confidence score. So if you predicted 4 boxes, you sort the boxes based on confidence score, but at the same time, you remove certain boxes with very low confidence because you anyway don't care about low confidence predictions. Because if you reduce your confidence threshold, maybe you will get 100 boxes. Maybe 90 of those boxes are with 10% confidence. So if your model is telling you that, hey, there is a bounding box in this particular location of the image, but I'm only 10% confident that there is an image inside this box. Will you take that box or not? You don't care about that box. You don't care about low confidence predictions. So first is you remove low confidence boxes below a certain threshold. So first problem here is, how is this threshold decided? Again, it is human engineered. People decided. It's not based on first principles. It's based on simple trial and error. So people will decide, okay, I don't want to consider any boxes below 0.3 or 0.5 confidence score. Then among the remaining boxes, you sort those boxes. Now let's go back to our example. So in this case, let's say my confidence threshold was 0.3. It should be above 0.3. Then what will happen is naturally this box will be eliminated. So this box is now not even in the question. Now I have 3 boxes, a box with 0.9 score, a box with 0.85 score, and a box with 0.7 as the confidence score. Now what do we do? Now I want to figure out, just based on mathematics, which are the boxes that now I should retain. Now what we do is we first pick the box with the highest confidence. So in our case, the box with highest confidence was the one with 0.9. So now this is the box with the highest confidence. All right. this 0.9. The second highest confidence guy is this 0.85, this box. So now what we have to do is we pick the box with the highest confidence, and let's call that as B1. That will be a contender in our final output list, meaning the box with the highest confidence will be one of the boxes that we will consider to be a good prediction. But then what we will do is we will compare this B1 with the remaining boxes. So now let's compare B1 with the remaining boxes. So B1 is compared with, so this is B1, okay? And let's say this is B2 and this is B3. So now B1 will enter our final list. We'll say B1 is our highest confidence box. So that is retained. We are not removing it. But now B1 and B2 are compared, and B1 and B3 are compared. Can you tell me what is IOU? First of all, IOU is a term that is used to define how much these boxes overlap with each other. So IOU is called intersection over union. I'll show you a figure. So IOU is area of intersection divided by area of union. So this area divided by this blue shaded area. If two boxes are having zero overlap, IOU will be equal to 0. If two boxes are overlapping perfectly, IOU will be equal to 1. If the overlap is in between, IOU will be somewhere in between. Now think about this. If IOU between B1 and another box is extremely low, okay, let's consider two boxes. Don't think about B2, B3, but let's say B1, I have box B1 and Bn. And let's say IOU between these boxes are like 0.1 or 0.2 or something like this. Okay. What we want to predict is we want to predict unique, high confidence boxes, unique boxes that have high confidence, because we want to predict unique objects. Now, my question is, we already rejected all the low confidence boxes. So every box is below 0.3 confidence is removed already. And now B1 is our highest confidence box. Bn is our nth box. In terms of confidence descending order, Bn is the nth box. And what I'm telling you is IOU between B1 and Bn is somewhere between 0.1 to 0.2. We already decided that B1 we are not neglecting. B1 is part of our final prediction because B1 is our highest confidence box. My question is, based on IOU, will you eliminate Bn or will you keep Bn? That's my question. For those of you who said keep Bn, why do you say you should keep Bn? Because B1 and Bn are anyway both kind of high confidence boxes, because low confidence boxes are removed. And the overlap between B1 and Bn is very low, which means it's very highly likely that box B1 and box Bn are bounding boxes around two different objects, not around the same objects. So B1 and Bn are not duplicate predictions of the same objects. They are very likely different objects being predicted. But what if B1 and Bn had, so here itself, just look at the example. What is the IOU between B1 and B2? IOU between B1 and B2 is 0. IOU between B1 and B3 is 0. Now, those of you who said eliminate B1 based on low IOU score, think about this. Will you eliminate B2 compared to B1? If you are comparing between B1 and B2, will you eliminate B2? You will not eliminate B2 because B2 is probably predicting completely different object altogether. B3 is predicting completely different object altogether, right? So what you do is you look at B1 compared with every other boxes. If there is a box which has high overlap with B1, so for example, let's say the confidence of this guy was not 0.3, let's say this was 0.7, right? Then overlap between B1 and let me call this as B4 for simplicity. If B1 and B4 are compared, their IOU is very high because the intersection is this much. Union is not so much higher than intersection. So IOU is very high score, which means B4 will get eliminated in the process. B2 and B3 will not get eliminated because when you compare B1 with B2 and when you compare B1 with B3, there is no overlap between them. So based on IOU, they are not going to get eliminated. However, this step we have to repeat again. Now B4 is eliminated. B1 is already finalized. Then you look at the remaining boxes. Now, what are the remaining boxes? B1 is already finalized. B4 is eliminated. Now you have B2 and B3 to look at. Now, which is the highest confidence box among these remaining ones? B2 is the highest confidence box. Then you compare between B2 and B3. So I'll explain once again. Your goal is to eliminate duplicate boxes. Why? Because you only want one bounding box around one object. You don't want two bounding boxes around the same object. Now, when during inference, anchors are getting converted to predicted boxes, which means there may be multiple boxes that may look like similar. There will be multiple other boxes which are different from some other boxes. So now you have to predict which boxes are actually not duplicates, which are the actual boxes that you care about. So first you look at the confidence scores of every box. You sort the boxes in terms of confidence score. You eliminate all the boxes with low confidence because you don't care about low confidence predictions. Then among the rest of the high confidence boxes, you pick the highest confidence guy and finalize it. So here the highest confidence box was B1. So B1 you are not going to eliminate. Now you compare every other box which are remaining with B1, and whichever boxes have very high overlap with B1. And how do you define very high overlap? Whichever boxes have a threshold above IOU value with B1, you eliminate those boxes because whichever boxes have very high overlap with B1 are likely duplicate boxes, as you can see in this image. Here B1 and B4 are probably predicting a person, probably bounding boxes around the person. B2 and B3 are probably boxes around a cat. But you don't need two boxes to predict one object. You need one box to predict one object, and you want the best box. You don't want the second best box. So now what you do, you compare B1 with B2, B3, and B4. And you see that B1 and B4 have very high intersection over union. Maybe IOU score is 0.8. I don't have the exact numbers, but you can see that intersection between B1 and B4 is very high, which means IOU between B1 and B4 is very high. And that for that reason, you eliminate B4. Why? Because B4 is very likely a duplicate box that is predicting what B1 has already predicted, but at a lower confidence. Now, once B4 is eliminated and B1 is finalized, now you look at the rest of the boxes. What are the remaining boxes now? Remaining boxes are B2 and B3. From the remaining boxes, again, just like how you picked B1 because it has high confidence, you pick from the remaining boxes the highest confidence box. What is the highest confidence box now? B2. B2 has 85% confidence. Now you again repeat the same thing. B2 and B3 you compare. Does B2 and B3 overlap significantly? Yes. Which means should you eliminate B3? Yes, you should eliminate B3. But if you had another box called B5, let's say this was B5, will B5 get eliminated? And let's say the confidence here was 0.6. Will B5 get eliminated when it was compared against B1? It will not get eliminated because it has no overlap. Will B5 get eliminated when it gets compared against B2? It will not get eliminated. You don't know whether there is an object here or not because you are doing inference. You don't have ground truth. You can visually see, of course, but algorithm does not know. Algorithm just knows which boxes are far apart and which boxes are duplicates that are not far apart, which are confident boxes and which are not confident boxes. So B1 is when it is compared against all the other boxes, B4 will get eliminated because B1 and B4 has very high overlap. Then we will move to B2 because B1 is finalized, B4 is gone. Then next highest confidence box is B2. If B2 is compared against B3 and B5, B5 will not get eliminated, but B3 will get eliminated. Now what is remaining is only B2 and B5 and B1. B2 is finalized and only thing that is remaining is B5. B5, there is nothing to compare against it and its confidence score is anyway higher than our threshold. So among the 5 boxes that were predicted, only B1, B2 and B5 will survive. B4 and B3 will be eliminated. These are called non-maximum, basically non-maximum suppression. So the NMS is basically, it's almost like a hand engineered technique. Where is the hand engineering coming? In 2 places, in deciding the confidence threshold and in deciding the IOU threshold. The numbers which are used for the threshold here are simply hand engineered, meaning we humans decide. It's not coming from any foundational idea. It's just a human engineered technique. So this NMS was one way to first predict large number of boxes and then eliminate boxes that are duplicates, right? And this was being used in many architectures before. And detection transformer very cleverly eliminates this non-maximum suppression. It also eliminates anchors. So we will see if non-maximum suppression is, if anchors are not used, then what else is being used in detection transformer, that we will see. So detection transformer actually uses a word called direct set prediction. So if you look at the abstract of the paper, somewhere they are mentioning, we consider this as a direct set prediction problem. Or a set-based global loss, somewhere in the introduction or somewhere in the abstract, they make use of this term called direct set prediction. So essentially what direct set prediction means, detection transformer will predict always a certain number of objects. So the number of objects is always fixed. So in the actual detection transformer paper, I think it was 100. So it will predict 100 objects, always, irrespective of what image you feed. Now you might think, what if in my image there is only one object? Then what happens is, out of the 100 bounding box rectangles that detection transformer predicts, only one will correspond to the object. Remaining 99 will correspond to background. So basically, there will be 100 boxes that are predicted. Only one will enclose the object properly. Remaining will be enclosing places in the background. So what do we mean by background? Isn't everything background? But background is something like this. So here, if camel is the object, this is how the one box which correspond to object will look like. And these are all boxes that are basically background. So detection transformer, what it does is, first, in an image, first of all, we don't care about predicting thousands of objects. So we have to first decide maximum how many objects are we interested to predict in any image. Maybe 20, 5, 50, something like that, right? We normally don't want to draw 1,000 bounding boxes around inside an image because it's not useful. So firstly, detection transformer decided that, okay, so I will say the maximum number of objects that I am going to predict is 100. And then, so that is called as a set. So it is predicting a set of 100 bounding boxes. And not just that, it can, because this 100 is a much higher number than the potential number of objects that will be present in an image, it doesn't matter whether in your actual image, whether there are 3 objects or 5 objects or 6 objects. So for example, in this image, there are 2 camels actually. So what will detection transformer prediction look like? It will look like there will be 2 boxes. There will be 2 boxes, one around camel number 1, another around camel number 2. And rest of the boxes will actually be such that they are in the background. They will be boxes which are enclosing pixels that are part of the background. So there will be 98 such boxes. So this 100 number was again a little bit not arbitrary. It was chosen because maybe in most of the object detection data sets, you don't encounter large number of objects per image. Here, there are no anchor boxes, by the way. Here in detection transformer, there is no concept of anchor box. I will tell how the box prediction happens. But basically, in detection transformer, the predicted boxes, you can have variable number of objects. And this variable can be anywhere between 0 to 100. The boxes can be with any shape, any aspect ratio, at any position. And we will see how this prediction is done. So the reason why it says direct set prediction is, detection transformer does not start from a certain set of anchors and then changing the anchor values through regression and then eliminating some of those modified anchors using non-maximum suppression. None of that is done. It predicts a certain set of number of boxes, and it tries to match each box to a unique object. If the number of objects is less than 100, which will be in most cases, of course, what it will do is 5 unique boxes will be, let's say 5 is the number of objects. 5 uniquely predicted boxes will be assigned to those unique objects. Remaining 95 boxes will be assigned to background. Now, there are a few things which you can only understand when we visualize this whole process. So that is what we are going to do. And you may also have, I'm sure at this point you have a bunch of questions, like how does the box matching look like? What is the ground truth? How are the predictions matched with the ground truth? how is the loss function constructed. So there is a very interesting loss function, which is probably one of the most interesting loss functions that I have recently come across, called Hungarian loss function, Hungarian matching. Hungarian algorithm is something that has existed before, much before deep learning. So we will also understand in today's lecture what exactly is this Hungarian matching. So I have dumped a bunch of terms on you right now. I'm aware of it, but we will go through it sequentially. So I have dumped the term NMS, anchor boxes, Hungarian matching, set prediction. So don't worry about all of this. I hope anchor and NMS is somewhat clear. Now we'll come to what exactly does detection transformer do with respect to architecture. So now we come to the architecture of the detection transformer. So first I will show you the diagrams from the paper. So this is from the paper figure 1. It's simple, but it may look intimidating, but I'll go through it step by step. In the first step, you have input image. In the second step, you have a backbone CNN. So this is where convolution operation comes into picture. This convolution operation is used for extracting spatial features from the input image. Then those features are passed through two blocks, one with transformer encoder and one with decoder. We'll get into the details of this, but this is just an overview. Okay, so this image is just an overview, bird's eye view, BEV. Input image, CNN backbone, like ResNet 50 or ResNet 100, pre-trained. So this is a pre-trained CNN, okay, pre-trained on ImageNet or any other dataset. It extracts the features. Those features are passed, tokenized and passed through transformer encoder and decoder. We will see how this looks like. And then it predicts this set of boxes. How many sets? 100 or whatever the number we decide. But basically that number will be fixed. And then what they are showing here is, just zoom in on this image. Here, actually, there are totally 2 boxes in the ground truth. So this is the ground truth. So you only need 2 boxes. So look at the color here. So what has happened is, what is this image trying to show is, this box and this box, this red box and yellow box will be matched to ground truth objects. This will be matched to background. So because this green is a background box. For the rest of the, and these are actually something called queries. So I'll come to that. Just remember the term. These are called object queries. I will come to the details of all of this, but just focus on what is happening. Each object query is corresponding to either a box or no box. No box meaning no object. So here, this black color query, blue color query, and yellow, or this, whatever this color is, that query is corresponding to no box or no object. This green color query is corresponding to the background box. This red and yellow color query are corresponding to the object boxes. So these are the 2 objects that we are looking at. So somehow what we are trying to do is, we are teaching these queries to predict the appropriate boxes. We will see the details. So just understand this much first. From an overview, maybe we can say there are 4 parts. Part 1 is the CNN. Part 2 and 3 are the transformer encoder and decoder. Part 4 is where this matching happens. So now we look at this sequentially. So first is, we have to discuss about this set prediction, what this direct set prediction problem. How does the input look like? What the model looks like? What does the output look like? And what is this Hungarian loss function or Hungarian matching? If we understand all of these things, we can understand the whole model. Now, this is another image, which is slightly, it is still zoomed out, but not as zoomed out as the previous image. I think this was the figure 2 of the paper. So here, what it starts, I mean, it's showing the same thing essentially, the CNN backbone, feature extraction. Then this features to the features which are tokenized, you add position embedding. We'll come to the position embedding. There are some details which you should notice about the position embedding, but I have my own versions of the figure, which in my opinion is a bit easier to understand. Then you have, so this is part 1, backbone, part 2, encoder, part 3, decoder, and part 4, prediction heads. Now, we have to go a bit more slower. We have to go through this part by part, but just try to understand that decoder does something where object queries are initialized here. Encoder does something where the tokens that are coming from image features are converted to context vectors. Okay, just broad level, in broad level, just think about these things. Details we are yet to look at. We'll look at it in a moment. And then prediction heads will take care of converting these transformed object queries into predicted boxes. All right, so now let's look at detection transformer architecture in parts. So first part, you convert your input image through ResNet 50 or ResNet 101 retrained neural network into feature map. Feature map will have certain height, certain width, certain number of channels C. In general, you might have seen that here there will be some height, width, and 3 channels, RGB. But features typically will have lower spatial resolution, more number of channels, maybe 64 channels or 128 channels. This is what you have seen generally. So feature map, whenever we hear about feature map, you have to imagine a multi-channel feature map, okay, not just one channel. Usually this will be large number of channels. So you're taking abstract features from the image and you are trying to make use of those features for your prediction. So part 1 is probably the most straightforward part because we have discussed this many times about transformer architecture. Now, part 2, not transformer, about CNN architecture. Now, part 2 is where we have encoder, transformer encoder. Now, transformer encoder also, this part needs to be zoomed in. We will look at this in a zoomed in view in some time. But in general, you know what is a transformer encoder. It will have a bunch of transformer blocks. Each transformer block will have layer normalization, multi-layer perceptron, residual connections, multi-layer perceptron, multi-head attention, residual connections, again layer normalization, again multi-layer perceptron, again residual connection. This whole thing enclosed in one single thing, which I will show you as an image. But basically, that is what is there in one transformer block. And those blocks are added in series inside the transformer encoder. I will zoom this in and show you in a bit. But right now we are zooming out slightly. So feature map is first converted into sequence of grid cells. So you convert the grids, each grid cell of multi-channels into single channel. You convert almost like patches converted to tokens. So here you have sequence of tokens. Now, what are these tokens converted into through transformer encoder? These tokens are converted into context vectors. So each token will be converted to corresponding context vector. Now, these context vectors are much richer in information, right? This is just like how transformer for InVision transformer or in any other transformer works. So feature map is, yes, feature map is flattened. It is divided into certain cells and it is flattened. But the number of here itself, it has a certain height, width, and number of channels. So by the time it reaches here, what is done is h comma width comma embedding dimension, or I can call it as B. So basically, the total number of vectors will be h times W, and the dimensionality of each vector will be D, where D is the embedding dimension in the in my transformer encoder. So basically, extract feature map using CNN, convert the dimensionality into whatever dimensionality is used in the transformer, and then convert the feature map into sequence. Converting into patches are not required because already the feature map is of very low spatial resolution. So I just drew these grid lines just to make you understand that whatever is there, it's like converted into a sequence, right? You are not explicitly converting to patches. Converting to patches would have been required if you are starting with an input image with high spatial resolution. Here you can directly, the total number, you can assume that each patch is 1 by 1 in resolution. So yeah, I mean, in a sense, it's patchifying, but only 1 pixel per patch, 1 by 1, something like that. But what you are doing here is you are converting the feature map, which was looking like H, W, C, where C is the number of channels. You project it through a projection layer to convert into H, W, D, where D is the embedding dimension. So now you will say you have H times W, that many grid cells in the sequence, and the dimensionality of each of those will be D dimensionality. So you have now tokens, H by W number of tokens, and then you have D as the dimensionality of each of those tokens. What happens to tokens when it passes through transformer encoder? Tokens are converted to context vectors. And inside this transformer encoder, there are multiple transformer blocks. Okay, transformer block number 1, block number 2, n number of transformer blocks. So basically, it will become a richer and richer context vector. So this is roughly what happens in transformer encoder. We will look at this in a slightly more detail in a little bit. Now, part 3. So now this is the output which you get from the transformer encoder, right? So of course, this output has to go into the input of transformer decoder. Where else have you seen encoder, decoder? In the attention is all you need paper. You might remember left side was encoder and right side was decoder over here. So this, let me copy paste this. So this left side is encoder, right side is decoder. So basically this paper was released not so far away from attention is all you need paper. Now in part 3, you have actually 2 inputs. So transformer decoder is part 3. It has 2 types of inputs. One type of input is called object query. Another set of input is whatever output comes from the encoder. So what is the output that comes from the encoder? This guy. These context vectors corresponding to your grid cells. So they are coming here. They are one set of input into the transformer decoder. Another set of input is object query. Just like this, where is the attention is all you need. Let me paste it once more. So here, look at this. Inside the decoder, into this multi-head attention, there are 2 types of input coming. One input is coming from this part of the decoder, as you can see here, and this is the query. 2 inputs are coming from the output of the encoder. This is the output of the encoder, and this is key, and this is value. I will explain this in a bit more detail, but I'm just first showing you the parallel between transformer, encoder, decoder, and attention is all you need, and here. But I plan to go into details of this. So don't worry if you don't understand some things very clearly. I know you have not understood something very clearly because I'm yet to show you the fully expanded figure. But just focus on decoder. So decoder takes encoder output as one set of inputs, and it begins with object queries. Now, why are we calling this as object queries, and what are these? So these are initialized as 0 vectors of dimensionality same as that of the dimensionality of the embedding space. So if your embedding space is, let's say, 768 dimensions, these object queries are a bunch of vectors initialized as zeros, and they are also, by the way, learnable. So the values of those vectors will be learnable through training. But now the more important thing that you have to notice is that the number of bounding boxes that you predict, including, and when I say number of bounding boxes, I'm also counting no object. So boxes plus no object or null. So this is called null box or phi. I don't even know if it is right to call it as a box, but number of boxes plus these null objects, the total number of these that are predicted will be equal to, according to this diagram, it will be 5. So how many ever number of queries you have, that is the maximum number of objects your model will be able to predict. So now if you have, 4 in this case, my bad. Now, if you want to predict 100 objects maximum, you should start with 100 object queries. Okay. So that is the first thing to notice. So the number of objects that you can maximum predict in your image will depend on the number of object queries that you have, which means these queries are now somehow getting transformed into bounding boxes. Okay, so that is now what we are going to see. So just let me reiterate that sentence. Object queries, which are vectors of same dimensionality as that of the embedding dimension inside the transformer encoder decoder blocks, those object queries are now responsible for transforming themselves into the bounding boxes. Some might be actual bounding boxes, some might be null boxes, which predict no object. Now you should have some questions. Now, what about encoder output? Because in encoder output, actually the number of tokens are, let's say, dependent on the feature map spatial dimension. So let's say the number of tokens that are there here is 20. So here, how many tokens will come? How many context vectors will come? A sequence of 20 context vectors will come. But here, the number of queries that are coming are 4, right? So far, this we have never discussed in this code. So far, whenever we constructed attention was query.key transpose divided by square root of D, softmax of this, multiplied by value. This is how we constructed attention. In all the cases that we have discussed so far, as far as I remember, the number of tokens, you had a sequence. So let's say the dog chased the ball or something. You had a sequence which was converted to tokens. So here you have 5 tokens. This token was converted to query key value. This token was converted to query key value. This was converted to query key value, right? So the total number of queries and keys were exactly the same. So here you have 1, 2, 3, 4, 5 queries and 5 keys. But here suddenly you are seeing there are actually 4 queries. So number of object queries are 4. But here the context vector has now the 20 tokens in its sequence, right? So how do you deal with this? So keep this question in your mind. We are going to look at it. Okay. So just let me step back. Part 1 is ResNet backbone. ResNet backbone will extract features. Part 2 is where features are tokenized. Those tokens are passed through transformer encoder to be converted into context vectors. Those context vectors, along with object queries, are fed into the transformer decoder. And transformer decoder will do something. We are yet to see what is that. It will do something to convert the object queries, of course, with the help of encoder output, because this has to be used. But transformer decoder will convert the object queries into bounding box predictions somehow. So now that is the last part. So last part is these object queries converted into bounding box predictions through multi-layer perceptron. So this FFN is feed-forward network, but basically it's a multi-layer perceptron which will predict 2 things. So actually there are 2 multi-layer perceptrons. Here, the way I have drawn it, which is very similar to the way the people have drawn this image in the paper, will make it look as if there are 4 feed-forward neural networks. That's not the case. There are actually only 2 feed-forward neural network. So this is MLP for predicting class, and this is MLP for predicting box. So these 4 object queries will pass through these 2 multi-layer perceptrons. So this class MLP is responsible for saying whether this box is responsible for whether that box is corresponding to cat or background or something else. Yes, I'll come to object query because I have to spend a bit more time in object query. But let me show you this last part and then we'll zoom in a little bit. The class MLP is responsible for saying whether object query 1, object query 2, 3, etc. are corresponding to cat, dog, background, etc. MLP for box is responsible for drawing the box. So whether that corresponding box is in this position or slightly to the left or slightly to the right, etc. Okay. So totally 4 parts. Part 1 for extracting features, part 2 for converting extracted features to context vectors, part 3 for converting queries with the help of context vectors into better representations, which is using a transformer decoder, and part 4 for predicting objects using the transformed object queries. Now we have a bunch of things to discuss here. Where is the loss function? What are these object queries exactly? How does the multi-layer perceptron look like? Where is position embedding added? There are a bunch of questions. So we have to go through all of that. Right now, this is just a high-level overview. And at the end, if there are 4 boxes predicted, right, we have to compare it with the ground truth. So we have to figure out what kind of loss function are we going to construct. So at the moment, okay, let me zoom out and just show you this overall. This is just combining the whole thing into one single architecture. Input image, ResNet, feature map, tokenization, context vector through transformer encoder. Context vectors are going into transformer decoder along with object queries. Queries are refined here, and then those queries are passed through 2 MLPs, one for class and one for box, to finally predict the class and box. So overall, it looks very simple, but we are still left with a bunch of questions. So these are the questions. How is the loss function constructed? What exactly are the query key and value in this case? What exactly is the object query? Is there position embedding? Where is that? How is that added? What exactly does our MLP or feed-forward neural network look like? We did not zoom into the encoder and decoder. How do these two things look like? What happens to this? I think we discussed a little bit. What happens to the output dimension after CNN? So output dimension after CNN will be number of channels, but those number of channels are then projected into embedding dimensionality. So this briefly we have discussed, but we have to go through all of these. Now, there are a few different things which I want to discuss before we go into this, which is very interesting. Okay. Let me decide. Actually, let me show you the architecture first, and then we can go through the loss function. So this is the encoder part. So CNN part is very easy. I don't think I need to spend too much time on this. This is the encoder part. So transformer encoder, the whole transformer encoder is consisting of bunch of transformer encoder blocks. So what is the input into the transformer encoder block? The starting input is the tokenized sequence, which is obtained from the feature map. Now, inside each transformer encoder, so this is one transformer encoder block, so there will be n number of blocks. Okay, so I'm zooming in on one of them. You know already what is this? Layer normalization followed by multi-head self-attention. This is the residual connection, then followed by layer normalization, multi-layer perceptron with residual connection. So this is basically one transformer encoder block. Like this, there are few transformer encoder blocks in series inside the entire transformer encoder. So now what comes out of this, you know that after each transformer encoder block, you will have a transformed token sequence, right? The context vector will become richer and richer and richer. So by the time your sequence of context vectors reach here, you will have a very rich set of context vectors. Now, one thing we can try to understand here is where exactly is the position embedding coming? So that is what I'm going to show you now. Don't get intimidated by this picture. I will exactly talk about what this is. I think we had briefly mentioned in the transformer part, this was few lectures ago, that the position embedding that is used in the original transformer paper was something called as sinusoidal position embedding. Sinusoidal position embedding meaning it's not necessarily a learnable position embedding. It is a position embedding based on a sine formula. So I can just show you the formula. Sinusoidal position embedding. So the position embedding was created using a formula that looks like this in the transformer block. So, and the values of those position embeddings, which are unique, can be plotted on a graph like this. Basically, it's not a learnable position embedding. It's a fixed position embedding. So here also, the authors used sinusoidal position embedding when we are looking at this sequence of tokens. Okay, so these sequence of tokens, first of all, we have to convert those tokens into query, key, and value. So sinusoidal position embedding is added before converting it to query and before converting the token to key, but for value, it's not added. So just look at this diagram. So you have sinusoidal position embedding value, and what will this value depend on? It will depend on the spatial position. So this spatial position is 0, 0. This is 0, 1. This is 0, 2. So you can construct two sine functions, one sine function to take care of x coordinate, one sine function to take care of y coordinate. And I think you can concatenate those two to create a sinusoidal position embedding whose dimensionality. So what should be the dimensionality of this added position embedding? It should be whatever is the dimensionality of your embedding, input embedding. So if the D model is 768, your sinusoidal position embedding should also be 768 dimensional vector. Otherwise, you can't add it. Now, this position embedding is added in query and key, okay? And then this query, key, and value is what is going into your multi-head self-attention. Now, one important thing to notice here is in the architectures that we have discussed so far in this course, the position embedding was injected only once, right? It's only injected at the starting. Or sometimes in swing transformer, it was injected inside the formula. Like if you remember relative position bias, it was like softmax of query key transpose by square root of D plus there was a position embedding Bij term. qi kj plus mask ij. So here position embedding was added after converting the tokens to query and key, and this was the relative position embedding. This was in swing transformer. But usually in most of the other transformers that we have discussed in this course, position embedding is added before query key transformation, just like here also. But it's only done once usually. But here in detection transformer, what the authors did is they injected the position embedding not just before the very first transformer encoder block. They injected it in the second transformer encoder block. They injected it here, here, and in all the transformer encoder blocks. Usually it is done only once, like at the starting. So this is one difference. So let me just try to understand. Yeah, in general position embedding. So here what is done is it was done corresponding to every multi-head attention. In general, position embedding is added over here. The tokens, you will have tokens, and then to the tokens, position embedding will be added. I think the reason why position embedding is injected in all the transformer encoder block is maybe to make sure that the model remembers the spatial information throughout the transformer encoder block series. I think that's the qualitative reason, excuse me. What is the intuition of not adding it to V? Because attention, so position embedding is primarily needed for calculating attention, nothing else. And attention is calculated using dot product of query and key, attention scores and attention weights. So that is why position embedding is needed only for query and key. Okay, so this is what is the only thing I would say which you might find different from all the other transformer encoder blocks that we have discussed so far. So the position embedding part of the transformer encoder, that's it. Now let's look at the decoder. Decoder is a little bit more complicated. So here, please pay good attention. So into the decoder, as we discussed, so this time I'm flipping the decoder from top to bottom to top. So previously input part of the decoder was here, output part was here. Here, just for the convenience of drawing, just consider that the flow is from bottom to top, okay, like this. It's just for my personal convenience of drawing, nothing conceptually different. So decoder has just like, now let me show you this diagram. Just look at this diagram. Decoder has, first of all, a multi-head, mass multi-head attention here, another multi-head attention here. In encoder, you had only one multi-head attention repeated n times in series. I mean, one multi-head attention in the transformer encoder, but then that transformer encoder block was getting repeated n number of times. Here, the transformer decoder block has two multi-head attentions before the multi-layer perceptron. So this is MLP, this is multi-head attention, this is multi-head attention, but these two multi-head attentions have there is a difference. So that is what we are going to discuss now. And hopefully at the end of this lecture, you will also understand this figure in a better way, right? So let's spend some time on the decoder. So in decoder, we have object queries. We also have outputs, which are context vectors coming from the transformer encoder. So now two interactions should happen. First is these queries themselves should interact to create an attention. These set of context vectors, they already went through transformer encoder, which means they already have, the global attention already has been baked into the context vector. Do you understand what I mean by that? The context vectors are created from image feature token. I mean, features converted to tokens. They were already passed through a bunch of transformer encoders in the transformer encoder part, in the transformer encoder block, which means global self-attention is already baked into this. So if this token and this token should pay very high attention to each other, it's already taken care of because these context vectors are already having that information. But queries are now initialized randomly, right? Which means this query, how do you know this query, the context vector corresponding to this query and this query should have high attention, or not context vector, this token corresponding to query number 1 and query number 4. How do we know how much attention they have to pay? So somehow some attention has to be constructed, self-attention has to be constructed between queries themselves to make the queries enriched in the context. That is first thing. Second thing is, now queries should interact. These are object queries. These object queries should now interact with the incoming context vectors from the transformer encoder output. So some kind of attention has to be constructed between the object queries and the transformer encoder output. So this has two different names. So when you are constructing attention between query with itself, when I say query, please don't imagine this cube. That is not what I'm saying. Here, when I say query, I mean object query. So these are called object queries, which you can simply imagine as bunch of vectors initialized as zeros. So object queries, first of all, should be enriched into better context vectors by having self-attention within itself among those object query tokens. So for that, you have a self-attention module for after a layer normalization. So this is one transformer decoder block. So you have layer normalization followed by self-attention, and you have a residual connection here. So by the time it reaches here, by the time these object queries reach here, they would have get converted into better context vectors. But there is one detail which I want to note here. This diagram is completely ugly, which is why I'm going to start with a brand new diagram with no annotations. So object queries, these are object queries. They need to attend to each other, which means they should be converted to query key values. So object queries will be converted to query, to key, to value using WQ, WK, and WV. So this is self-attention where object queries are attending to themselves. Here it is written cross-attention, but I'll come to that in a moment. But here position embedding need to be added. So the kind of position embedding that is should not the object query start from the of course. So these lines that I'm drawing, okay, this line I'm drawing is not representative of the I just see if I draw this object query over here, my diagram will look like a bit confusing. So okay, I understand where the confusion is coming from. The only reason why I'm drawing it like this is to show that finally these after layer normalization are converted to query key values, right? So actually the way this goes is these three things will pass through layer normalization. Okay. And then it will get converted to query key value. So ideally I should draw something like this: query, key, and value. Okay. So I'm just drawing it as a shortcut here, but imagine that layer normalization has already happened. Okay. So please don't get confused. The count of object queries are number of objects you want to detect, like 100. Yes, correct. That's correct. Count of object queries should be same as maximum objects you want to detect in your image, or maximum objects you are expecting in your image. Okay, so now object queries should be added with the position information, because these queries are, this is query number 1, query number 2, 3, 4, etc. But here, these queries, there is no special position information that you know already, which means you can't use sinusoidal position embedding, because what is the meaning of the position number 1, 4, etc. here? There is no meaning. So you let the position embedding for these queries be learnable position embedding. So that is what is drawn. I have drawn in this figure. So you have learnable position embedding, which are added to the input token before getting converted into query, and before it getting converted into key, of course, through layer normalization. So I'm conveniently not drawing it by drawing a convoluted line here, but assume that layer normalization is done. Position embedding will be added before layer normalization. So, excuse me. So learnable position embedding will be added to query and key. Corresponding to object queries. Now, object queries will form self-attention inside the multi-head self-attention block to have enriched context vectors corresponding to object queries. Now, is that enough? It is not enough, because we need we need object queries to interact with the context vectors that are coming from the output of the transformer encoder. So now that we can draw here. So now what should happen? These object queries will go here. Now these are now outputs coming from the transformer encoder. They will also be converted to query key values. So now query key and value, and they should have a position embedding. Actually, let me erase one thing. There is one mistake in my drawing. They will not be converted to query key value. They will only be converted to key and value. Value and key. And queries will be the tokens, object queries converted into queue. So that is why this is called cross attention. So now look at this. The object queries will be converted using a WQ matrix into queue. But for key and value, you take the context vectors, which are the output from the transformer encoder. So the reason why this is called cross attention is because the sequence which ended up creating this queue is different from the sequence which ended up creating this K. The K is the result of the sequence which is from the CNN features. So CNN features were converted into token sequence. Token sequence became enriched context vectors from the transformer encoder. And now those are converted into or projected into key space. But for query, so usually in self-attention, query and key are in the same dimensional space, but they are projections of the same input tokens, same sequence of input tokens. So here, query is on the other hand in this cross attention, query is coming from the object query tokens. So they are projected into the query space. Key and value are corresponding to the these context vectors. And then you construct the cross attention. There are some questions. Okay, let me see. Wouldn't it make sense to take the object query which passes through the first transformer decoder block for doing the cross attention? Yes, that is correct. So you mean to ask, Shubhankar, shouldn't we take the enriched, shouldn't I draw it somewhat like this? Or rather something that passes through layer normalization? Shouldn't we take object queries which are from the context vectors, right? That is correct. So the only reason why I'm drawing it like this is to show that in the cross attention, at the end of the day, the origin of the query is not from the image, it is from the object queries. The origin of the key and value is not from the object query. The origin of the key and value is from the image, right? Then we are already getting enriched context vector of all queries from self-attention and then layer normalization. That will also go as input. That will also go as input to context. We are already getting enriched context vector of queries from self-attention and then layer normalization. Yes. So I'm so sorry for drawing like this, because if I don't draw it like this, the point that I want to make you understand is the origin of the key. The reason why this is called as a cross attention is because the origin of the query is not the same as origin of the key. Key and value here in this case originates from the image ultimately. Query here does not originate from the image. Query originates from the randomly starting, zero initialized object queries, right? On the other hand, here in the transformer encoder, query originated from the image, key originated from the image, value also originated from the image. So this is not a cross attention, this is self-attention. Because when you take dot product between query and key, the same sequence of tokens are now projected into the query and key space. Of course, it is after layer normalization, but I drew it like that to show you the origin. Where is it coming from? But here in this diagram, let me move to this. In self-attention, the origin of the query is from the object queries. Origin of the key is from the object queries. Origin of the value is also from the object queries. Are those object queries passed through layer normalization before coming to self-attention? Of course, yes. Then is there residual added after this? Yes. Is there layer normalization after this? Yes. So by the time your object queries reach here, so you have 4 object queries. Let me just draw 4 of them here. So you will have 4 here. You will have enriched context vectors. right? So now these are 4 enriched context vectors due to the self-attention, where now queries are paying attention, these object queries are paying attention to each other in these 4 context vectors. Now these context vectors are converted into queries. So the origin of the query, which is there in this cross attention, is ultimately these object queries. Similarly, origin of the keys and values is the image, but where is the key and value calculated from? It is calculated from the context vector which came out of the transformer encoder block. So the reason why this is called cross attention is because when you take q dot k transpose, q is coming from a different sequence and k is coming from a different sequence. Where is q coming from? Q is coming from the context vectors corresponding to object queries. K is coming from the context vectors corresponding to the image feature tokens. All right. And now let's look at this image once again. So now hopefully you will understand this slightly better than what you knew before. So look at this. So here you are having, so this is the decoder and right side is the encoder. So in the encoder, you have input token embedding, and those token embeddings pay attention to each other in this self-attention. And then finally, they are converted to context vectors here. So this is MLP, this guy, and this is the MSA, multi-head self-attention. Now, this is converted to value and key, but query is now coming from here, from the decoder input. So this is the query, and this is sort of like cross attention, and then query.key, softmax of this multiplied by value, followed by multi-layer perceptron, and then softmax finally for predicting the next word probability. So almost exactly this is what is happening, except the positional embedding. So here, position embedding is only added once. The sinusoidal position embedding is only added once here. But in our case, they added it at every, in the encoder, they added it at every transformer encoder block over here. This was sinusoidal position embedding. And here, yeah, I did not mention the position embedding added here. So in object queries, there is no inherent position information. So you are adding learnable position embedding. So plus learnable position embedding, LPE. There is no such term existing. I just made it up, but LPE, learnable position embedding, is added to query and key. Value, it's not added. For cross attention, can you tell me, are we going to add the same position embedding to Q and K in cross attention? For Q, we will add LPE or sinusoidal. Learnable position embedding. Learnable position embedding simply means you randomly initialize a position embedding vector, and through backpropagation during the training, the values of that position embedding vector will get modified. In sinusoidal position embedding, it's like a fixed position embedding vector. It's not learnable. And here, sinusoidal is added. Why is sinusoidal added here? Because this key is coming from your image sequence, which inherently had a spatial 2-dimensional structure. So there we don't add learnable position embedding. Do we need to add any kind of position embedding to the encoder output? Encoder output meaning, you mean here, right? I mean, essentially, this is the encoder output. Encoder output is converted into key and value. Yes. So encoder, the key that is resulting from the encoder output is added with the sinusoidal position embedding. Now, instead of showing my handwritten ugly diagram, let me show you a slightly cleaner diagram. Okay, so just don't get afraid. Let's go through this one by one. You have object queries, and object queries should pay attention to each other. So for the self attention, the origin of these object queries are origin of the query and key value vectors are the object queries themselves. And there, for query and key, we add position embedding, and all of this happens before layer normalization. Okay. So why do we add learnable position embedding for object queries? Because we don't know what is the spatial relationship between object query, anything. We don't know anything about object queries spatial relationship. They are literally 4 or 100 or 50, how many ever objects you want to predict. So object queries are you don't know what are the relationship between them. So it's even, in my opinion, not correct to call it as position embedding. Just call it as some learnable embedding. Whether it is learning position or something else, you don't know. But in usual literature, people find it easier to call it as position embedding. So that is added to query and key. Then not added to query and key, those are added to inputs before getting converted to query and key. Now in cross attention, query comes from object queries. So see this, query comes from object query, that is the origin. But in the cross attention key and value, its origin is from the context, this transformer encoder output, which is resulting from the image. But are these three things coming directly from here, or are they coming from layer normalization, self-attention, etc.? So this query is created using the context vectors resulting from layer normalization, self-attention, residual, etc. And then another layer normalization. So at only this point, you have 4 context vectors corresponding to these 4 object queries. Those 4 context vectors will be converted to 4 key vectors in the key space. This, no, sorry, not 4 key vectors, 4 query vectors in the query key value space. In the same query key value space, you will need key and value, so that you can take dot product between query and key. And this key is originating from your context vector corresponding to encoder output. Value is also originating from the same. However, please note that since the query is coming from your object queries, the position embedding here that is added is learnable position embedding. Since key is originating from the image where the position information is kind of known, you add sinusoidal position embedding. Okay, slightly complicated, but I think you will understand if you spend a bit more time. Context vector will directly goes to the cross attention head, or will it go via decoder block? It will be taken to the cross attention directly after projecting. Okay, tokens should be projected to query key value space, but it will go to the cross attention just like this, as you can see here. So here they are not passing through here, right? Here they are directly going into the multi-head attention. Same. Okay, so now what is there? Okay, now there is a very important thing which I want to discuss. So after all of this, when we make a prediction, this is what we want, right? Let's say I have 2 objects to predict in my image. If my image is like this, and if I had a person and a cat, okay, I only want to predict 2 bounding boxes in this case. But let's say I have 4 object queries. 4 object queries that look like this. But I have only 2 ground truth bounding boxes. So prediction, bounding box, B box. Now my question is, you want to match only one unique prediction to one bounding box. Because that's the whole point. That's the whole value proposition of detection transformer. There is no need for non-maximum suppression, because you are not going to predict duplicate boxes corresponding to the same ground truth. This is ground truth, bounding box corresponding to ground truth. So either you will say this prediction corresponds to this one, this corresponds to this one, and this correspond to no object or background, or let's say no object phi. Or you will say this corresponds to this corresponds to this, and this are corresponding to null objects. So what you do is, if you have 4 object queries, and in the ground truth, if you have only 2 boxes, you add 3 null objects, 5, 5, 5. So 3 null objects. So you have 2 ground truth objects and 3 null objects. Sorry, not 3, 2 null objects. Guys, just give me a second. There is a little bit of sound coming from outside. Just give me 1 second. Sorry about that. So what is done is, if you are having ground truth boxes, guys, just a second. Sorry about that. There is some drilling operation going on. I just had to ask them to pause for a bit. All right. So what we want to do is 4 predictions should be matched to 4 ground truth boxes, or 2 ground truth boxes and 2 null predictions, so that every object query is corresponding to one unique ground truth, right? So this is what we want to do. So basically, it's like a matching problem. So you predicted a set of boxes, and those predicted set of boxes now should be matched to some good ground truth boxes plus some some null objects. Now I'll show you what this means in in a bit better way. But the question is, how is this matching usually done? So in non-maximum suppression, how was the matching done to ground truth? If you wanted to construct the loss function, you will have finally a predicted bounding box. You will have a ground truth bounding box. So this is, let's say, the final predicted bounding box emerged out of the non-maximum suppression. This is the actual ground truth bounding box. You can construct some sort of loss function using IOU. You can say the preciseness of your predicted box with respect to ground truth box can be calculated based on IOU. But here, something unique has to be done, because you have to match one box with one prediction. You don't have the ability to predict large number of boxes and eliminate those duplicate boxes and then say that these are your final predictions. You can't say that. So I will show you this with a simpler example that explains Hungarian loss. So Hungarian loss is basically a loss function that is defined in context like this, where you basically try to have a set that is mapped to a set of other objects. So this is the example. Let's say you have 4 workers and you have 4 jobs to be done. Now these workers will quote different amounts of pricing for different jobs. So worker number 1, so let's call them red, blue, green, and pink. So this worker will have 4 jobs, and worker number 1 is quoting $1, $2, $3, and $4 to the job. Worker number 2 is quoting like this. Now let's say you are the person who is the contractor, and you have to assign a unique job to one worker such that your total cost is minimized. So you want to get job 1, 2, 3, 4 done. 4 jobs you have to get done. And to get those 4 jobs done in the most cost efficient way, you have to find which worker needs to be assigned to which job, right? So that is the problem that we are trying to solve. Now here it kind of looks easy to figure out the optimum, because it's an optimization problem. In the case of the bounding box matching, like which object query corresponds to which bounding box, also same thing applies, because you will have 2 ground truths and 2 null objects. So totally there are 4 objects. And then there are also 4 boxes that are being predicted, because you have 4 object queries. Now you have to match whether object query 1 corresponds to ground truth 1, ground truth 2, or 5, which is the null object. And you have to do it in such a way that the overall loss of the model is minimized. So here, there is a very nice trick or very nice sequence of steps that is done, that is called as Hungarian matching. So this name Hungarian came from the fact that the scientist who proposed, I completely forgot his name, he named it after 2 Hungarian scientists who were working on a similar problem. So the original algorithm from which this Hungarian matching came was called Hungarian algorithm. And the scientist whose name I unfortunately forgot, he named it after 2 Hungarian scientists who kind of laid the groundwork for this algorithm. So the algorithm is as follows. So first you create this, cost matrix. So this cost matrix is 4 jobs, 4 people. You have to find the unique job person pair so that all jobs are getting done. You can only assign one job to one person. So first is you subtract a minimum number from every single row. So every row, for every row, find what is the minimum number and subtract it. So for example, in row number 1, the minimum number is 1. So you subtract 1 from row number 1. So what does that mean? That means the red worker is reducing his cost, which is proposed for every single job, by $1. That's the meaning of that, right? Similarly, and now please tell me, if I reduce the cost of every single job, let's say my optimum job distribution that I as a contractor was, I gave job number 1 to this guy, job number 2 to this guy, job 3 to maybe this guy, and job 4 to this guy and job 3 to this guy. Let's say this is what I did as a contractor. Okay. Let's say I'm not saying this is the optimum distribution. I'm just saying if this was the optimum distribution, and let's say suddenly this guy reduced his quotation for all the jobs by $1. For job 1, he reduced the pricing from 1 to 0. Job 2 became 1. Job 3 became 2 and job 4 became 3. Does it change the optimal distribution? It doesn't change the optimal distribution. You can think of it logically, no need to think about it mathematically, because let's say it changed the optimal distribution, meaning because this guy has now changed the pricing of job 1, he can be assigned some other job. The benefit that this contractor is getting is not changing because the contractor already got the benefit. The -1, the benefit of reduction of the $1, the contractor is already getting, irrespective of whether this person was given job 1, 2, 3, or 4, because he reduced the pricing of all the jobs by $1. So that benefit is already baked in the current distribution itself. So if the current distribution was the optimal job distribution, that is not going to change because of the fact that this guy has reduced the pricing of all the jobs by $1. So by the same logic, I can then subtract any number from each of these rows. So from the row number 1, I can subtract any number. Row number 2, I can subtract any number. The number has to be constant throughout the row. As long as I do that, there is no issue of my optimal distribution changing. So now let's find out the minimum number from each of the rows. So the minimum number in this row is 1. So I subtracted 1 from the row. So the numbers became like this. Minimum number in the row number 2 is 1. So the second row became like this. For row number 3, again, minimum number was 1. So it became like this. Same for row number 4. So now you see one good thing that has happened is you see the cost. Now, when you see zero cost, it's easy to find the minima, because here you can see that for job 1, there is somebody offering 0 cost. For job 2, there is somebody offering 0 cost. It would have been very easy for us to find the minima if, for example, this was also 0. Because then all we need to look at is, for job 1, is somebody giving me 0 cost? Yes, this guy. Is job 2 somebody giving me 0 cost? Yes, this. Is job 3 somebody giving me 0? Maybe if this was 0, I could pick that. And same for job 4. Excuse me a second. So this is called as zero cost assignment. So if we can somehow convert the minimum cost of jobs to 0, we can easily pick the minimum total cost assignment. Because now if I assign job 1 to this guy, job 2 to this guy, job 3 to this guy, and job 4 to this guy, my total cost is 0 plus 0 plus 0 plus 0. Its total cost is 0. All the other numbers are positive numbers, which means I cannot go below 0. There is no negative cost. So if I can somehow come up with 0 as numbers in every row, then I can somehow easily figure out an optimal distribution. So now by the same logic which we applied here, I can also apply the same logic to column. If the pricing of job 1, let's say every worker number 1, 2, 3, 4, everybody reduced their pricing for job number 1 by $1. Does it affect the optimal distribution? It doesn't, because the market is not changing. The job 1 overall, all it means is to get the job 1 done, the contractor needs to pay $1 less, irrespective of which person this contractor picks. So now what we can do is we can subtract the minimum number from every column also, just like how we did for every row. You will soon understand why we are doing this step in the context of detection transformer. So this was what resulted after subtracting the minimum number from each row. Now from each column, for every column, first to third column, the minimum number is 0. So there is nothing to subtract. For the last column, minimum number is 1. So you can subtract 1 from all these numbers. So last column will now become something like this. So you subtracted minimum from rows, minimum from columns. So now this is your current cost, distribution matrix. Now what you do is you find this. This sounds a little bit like some geometric technique, but this is exactly how you can implement the Hungarian matching algorithm. Now you draw some lines, minimum number of lines, which will cut through every single zeros which you have in the table. So I can draw one line like this, another like this, and another like this. Now I drew 3 lines, and 3 lines are cutting all the 4 zeros, right? So I mean all the zeros in my table. So the number of lines, let's say, let us call it as M, is 3. But number of workers that I have to assign is 4. So let me show you this. So find the minimum number of lines that cross out all zeros in the table. So the minimum number of lines that are required to cross out all zeros are 3. But I have 4 people to assign jobs to. So now we have to repeat one more step, which is now look at from the remaining numbers which are uncrossed. What is the minimum number? The minimum number is 1. Now, if I were to subtract 1 from all these rows, the problem is some of these numbers will become -1. I don't want negative cost. I want the minimum cost to remain as 0. So what you can do is, first, you can add this 1, this minimum number, to all these crossed rows and columns. So I can add 1 here. So add +1, +1, +1, +1. So since I'm adding same number to the column, my optimum assignment will not change. Here also add +1. If minimum is 2, you add +2. And then here also you add +1, +1, +1, and +1. So now what happened is you have 1 added to these 3 cells, 1 added to these 3 cells, 1 added to these 2, and 2 is added to these 2, because row-wise, I mean column-wise +1 was added, row-wise also +1 was added. So here 2 is essentially added for these 2. Now what you can do is, now you can subtract this minimum number 1 from every single rows. So now if this 1 is subtracted, +1 and -1 will cancel each other, +1 and -1 will cancel each other. This 2 will become 2 minus 1, which is 1. This 2 will, again, -1 is added here. So 2 minus 1 is 1. So finally, your matrix will look like something like this. So here there is a mistake. Here there is 1. So your matrix will look something like, yeah, okay, it's 1 only. So matrix will look something like 1, 7, 4, 3, 2, 1, 1, 1. So what we have done is we have eliminated, not this. We have eliminated, this 1 also. So you wanted to subtract this 1 without introducing negative number. So to not introduce negative number, you add this 1 to this crossed out rows and columns, and whichever cells are getting double crossed by 2 lines, their value will increase by 1. For the rest of the cells, their value will not change because you are also subtracting this 1 later from every single rows. So at the end of the day, I know that I have told you too many number of steps, but if you zoom out and look at it, it's a little bit simple. At the end of the day, you will get something like this. You will see that every row has some 0 in it. So this row has a 0. So you can say a red person can be assigned job 1. Blue person can be assigned job 2. Green person can be assigned job 4, because this person is quoting. The green person cannot be assigned job 2. Why? Because job 2 is already assigned to blue person. What's wrong with green person assigning job 2? Because then blue person cannot take job 2. Blue person will have to be assigned maybe job 3. But then cost increased. by 1. So, and then green person can be assigned job 4, and this pink person cannot be assigned job 2 or job 4 because those two jobs are already taken, but the pink person can be assigned job 3. So now the total cost of doing this job is 0 in this zero cost assignment, 0 plus 0 plus 0 plus 0. But to know the actual total cost, you bring back your original matrix. So your original matrix was this. So let me copy paste it here. So your actual total cost will be corresponding to this 0, it was originally 1. So 1 plus corresponding to this 0, it was 1. 1 plus 1 plus 1 plus 3, which is 3 plus 3, 6. So this will be now the 6 is the now the minimum cost. 6 is now the cost that you can, go to, like in the minimum case. And to achieve the least cost of 6, you have to assign this red worker to job 1, blue worker to job 2, green worker to pink job 4, and pink worker to job 3. If you do that kind of an assignment, you will achieve minimum cost, which is 6. Now, why are we talking about this jobs and person matching and all? Because same thing is what is happening in our case, because we have a bunch of bounding rectangles that are predicted through our object queries, and we want to match them to a certain bounding rectangle because we don't know which predicted object query is which bounding rectangle. We have to come up with some parameter, right? So first what we do is we say that if I have two predicted bounding boxes, okay, this is, let's say, predicted bounding box 1 and this predicted bounding box 2 in the image. And let's say in the image, I have two ground truth bounding boxes, ground truth bounding box 1 and ground truth bounding box 2. Now, what I want to do is I want to minimize my cost by assigning this person one of these two jobs and this person one of these two jobs. So now you can think of the predicted boxes as people, the ground truth boxes as jobs. And I want to assign the correct bounding box to the correct ground truth so that my total loss is minimized. And to find the matching, you have to use some sort of Hungarian matching. Now the question is, here you were already given the cost. You already knew what was the cost. Here, what is the cost? So if these P1 and P2 are people, what is their cost? What is the cost of P1 for being assigned to ground truth 1? What is the cost of P1 being assigned to ground truth 2? What is the cost of P2 for being assigned to ground truth 1? And what is the cost of P2 for being assigned to ground truth 2? So we need to construct some sort of mathematical cost function. And then we have, yes, IOU is one. I mean, good example. IOU is not the only one, but I'll come to that. So first we have to construct some sort of cost for assigning prediction number 1 to ground truth 1 or prediction 1 to ground truth 2 individually. You also have to know the cost associated with assigning prediction number 2 to ground truth 1 or ground truth 2. And then once we have the cost matrix using Hungarian matching algorithm, we can figure out the optimal matching between all the predicted boxes and all the ground truth boxes. So this is what, can the number of ground truth boxes be more than the number of predicted? No, it can't happen, because that's why I said the object queries, number of objects queries is assigned to be a big number like 100, so that never the number of ground truth boxes will be greater than the number of predicted boxes. So that's the reason why here we took an example of 4 object queries, but in actual detection transformer paper, they use 100 object queries or something. Now, there is one more question here. When do you not need Hungarian matching? Let's say I have only one ground truth, and let's say I have 5 queries, 5 object queries. Do I even need Hungarian matching? No, I can simply take some IOU or something, right? If I just have one ground truth, and if I have multiple queries, if I want to find which query fits the ground truth the best, minimizing the cost, I don't need matching. I simply have to calculate the cost and find whichever has the lowest cost. But now let's say, when do you actually need Hungarian matching? Let's say I have 2 ground truth and 5 predicted boxes. What will happen is, so this is an example which I just wrote to make you understand in the context of detection transformer. So let's say now I am considering the prediction number 3. Okay, and I'm comparing that with, so I have 5 predictions and 2 ground truth. And now compare the prediction number 3 with ground truth 1, prediction number 3 with ground truth 2. And let's say I was just looking at IOU to perform the matching. What may happen is if I'm just looking at IOU, if I have ground truth 1 and ground truth 2, let's say these are my ground truth rectangles. And my 5 predicted boxes are like this. One box is, this is P1, this is P2, then this is P3, then this is P4, and this is P5. Okay, so these two are the ground truth. Now, if I'm only thinking about IOU, the problem is the IOU between G1 and P3 is greater than 0. The IOU between G2 and P3 is greater than 0. But IOU between G1 and P5 is 0, G1 and P4 is 0, G1 and P2 is 0, G2 and P5 is 0, G2 and P4 is 0. So now if I'm only looking at IOU, I will end up saying that this P3 box is the box that predicts both ground truth 1 and ground truth 2. But that's like predicting same box for 2 objects, which is not what we want. And this is happening because if we don't rely on Hungarian matching, and if we only look at IOU, and if we only look at the maximum value of IOU, we might end up predicting same box for 2 different ground truths. It may also happen that we may predict like not so great boxes. So here is one more problem. Let me show you something like, let's say, yeah. So one more problem is the IOU between ground truth 1 and P1 is 0 because there is 0 overlap between them. IOU between ground truth 1 and P4 is also 0 because there is 0 overlap between them too. But you can see that P4 is a very bad box if it were to be matched with G1 because P4 is so far away from ground truth 1. But P1 is kind of closer to ground truth 1. But if we are simply considering normal IOU, its IOU score is 0. Intersection over union for P1 and ground truth 1 is 0. P4 and ground truth 1 is 0. So we are not able to distinguish these boxes. So Hungarian matching is first done so that we can assign correct predicted boxes to corresponding ground truth boxes. And then we can calculate the loss, total loss. So now let's see how the total loss is calculated. So this is the detection transformer loss. Okay, so there are 2 losses. One is broadly, one is classification loss, second is localization loss. Classification loss comes from the fact that the model may draw a good bounding box, but model may say inside the bounding box, you have a cat instead of a dog. But that might be a wrong prediction. So for making mistakes in classification, in assigning the class, you have to penalize the model. Also, to kind of penalize the model for drawing the bounding box at the wrong location, you should have some loss. So that loss is based on 2. One is L1 loss and another is called global generalized IOU loss. So I'll come to this generalized IOU loss in a moment. But this is where I think somebody had mentioned about IOU loss in the context of what should be the loss function. Yes, IOU is coming into the picture, but in a slightly modified way. And L1 loss is simply this. You have 4 parameters that are getting predicted, X, Y, W, H. So L1 loss is simply X predicted minus X ground truth plus Y predicted minus Y ground truth plus W predicted minus W ground truth plus H predicted minus H ground truth. So this is sort of like L1 loss. So this is penalizing the model for making mistakes in the position of the rectangle. This is penalizing the model for something very interesting. I'll come to that in a moment. Classification loss is penalizing the model for saying that inside this bounding box, whose coordinates are x, y, x prime, y prime, w prime, and z, h prime, it is a cat instead of a dog. So yeah, I'll come to where is Hungarian loss here. So now let's look at this. Hungarian loss is coming in the fact that, first of all, how do you compare the prediction and ground truth? So here we are, when we are saying classification loss or when we are saying localization loss, We are comparing between predicted box for ith object and ground truth box for ith object. Now, how do I know which among the predicted box is the box corresponding to ith ground truth object? So to match, so if we are predicting 5 boxes in the prediction, and if there are 5 ground truths, first I have to match them. So for that matching, you have to use Hungarian matching. And once you have matched prediction ground truth pairs, and that for that, first of all, you have to calculate the cost of every pair, right? So you have to, if you have 5 rectangles here, actually you had 5 workers and 4 workers and four jobs. And you calculated the cost for every single worker for every single job. Similarly, this detection transformer loss, you have to calculate between every single predicted box and every single ground truth box, right? So you will have, just like how you have the quotation from every single worker for every single job, you will know what is the total detection transformer loss, considering 3 losses, the classification loss and the 2 parts of the localization loss, which is L1 loss and global IOU loss. You will know for predicted rectangle number 1 corresponding to ground truth 1, what is the total detection transformer loss? For predicting rectangle number 1 corresponding to ground truth 2, what is the total detection transformer loss? Like that, I will have, if I have 5 boxes to be predicted, which is predicted, and 5 boxes in the ground truth, I have 5 by 5, 25 total losses. Now, before calculating the total loss, I have to know which box made the correct prediction, like which box should be assigned to which ground truth. For that, you use Hungarian matching. So now this term, I hope you understand. Classification loss is simply if the class was predicted in the wrong way, you can take a softmax cross entropy loss. Localization loss has L1 and global IOU term. L1 is the most straightforward loss. Global IOU, let me show you. And then finally, the total cost is not simple addition of these 3 losses. So this is the loss due to classification. This is the L1 loss. This is the global IOU loss, which I am about to explain. This is the total localization loss. And they are added by weighting with these lambda values. So lambda values, the paper uses certain specific lambda values, but of course, we can try it as we can try different values as hyperparameters. Now, what is this IOU? The problem with or global generalized IOU, the problem with normal IOU is this. Let's think about these 2 cases, okay? Case 1 and case 2. IOU is 0, but we know that if this was ground truth and if this was the corresponding prediction, we know that case 1 is better than case 2, right? So just by taking IOU, we are not able to get a good representation of the fact that case 1 is significantly better than case 2. Then what can we do? What can we do is we can slightly modify the formula where generalized IOU is the actual normal IOU minus some extra term. Now, what is this extra term? It has something called as area of C. Now, C is area of this smallest rectangle enclosing both ground truth and predicted boxes. So now C is greater in case 2 than in case 1. Now look at this formula. Generalized IOU is IOU minus area of C minus area of P union G. P is prediction, G is ground truth, divided by area of C. If I simplify the formula, it will become IOU minus 1 plus P union G by C, because this, if you take minus with area of C divided by area of C, that will be minus 1. Then this minus and this minus will become plus 1. So plus P union G by C, okay? So anyway, IOU between ground truth and prediction is 0 in both of these cases. So let's say IOU is 0. So then this formula will become generalized IOU equal to minus 1 for this special case. I'm showing this formula for this specific case. Generalized IOU equal to minus 1 plus P union G by C. And now let's say the area of P and G was the same, right? So now we can say if they are the same, I can say P union G equal to 2P or 2G, right? By either of these I can call. So now generalized IOU will be minus 1 plus 2P divided by C. Now look at this formula. In which case is C greater, case 1 or case 2? C of 1 and C of 2. In which case is C greater? In case 2 is C greater. So C of 2 is greater, which means in the generalized IOU score will be bigger if the C value is smaller, right? And C value is smaller in case 1, which means generalized IOU score is higher for case 1. So essentially, generalized IOU is a better score to consider if you want to take into the fact that there might be rectangles that are initially far away, but you don't want to penalize two rectangles in the same way just because they don't have any overlap. So this is a better distance formula between the rectangles. So these are the three loss terms that are part of the detection transformer loss for calculating the loss between any two pairs of rectangles, any predicted rectangle and any ground truth rectangle. Then which pairs are finally considered? The pairs that are finally considered is based on the Hungarian matching. Now, okay, that is good. I just wanted to show one more thing, just one more detail, which I don't think I have mentioned. So I talked about the FFN, feed forward neural network. So forget about this. Let me put a rectangle here. So just forget about that. This feed forward neural, these are now the context vectors corresponding to object queries. Okay, these 1, 2, 3, 4, 5, 6. Now these context vectors are responsible for predicting the class and the box. Now, how do we predict that? These object queries are simultaneously passed through two feed forward neural network. One is for multi-layer perceptron for class. One is multi-layer perceptron for box. So this MLP will predict whether the item inside our box is whatever object is person or dog or cat or whatever. MLP will predict, and here it will be basically a softmax probability score like 0.9. So if there are only 3 objects in the training data, it will look like 0.9, 0.05, 0.05. Right? So then this itself can be directly used as the confidence score. Then box MLP will tell you what are the 4 coordinates of the box: h, w, x, y, w, h. And one interesting detail which I want to note, which is not a big deal, which even if you don't know, it's okay, is that just that during the training of detection transformer, they calculate the total loss by constructing the loss using every single decoder layer, not just the whole decoder output. So this layer will have a context vector output. This layer will have a context vector output. This layer will have a context vector output. Every single one of them will be a sequence of context vectors corresponding to your starting object queries. So using all those object queries from every single layer, every single transformer decoder layer, you can perform predictions. So each of those predictions will result in different loss. So those losses, so this loss is from this loss is from the transformer encoder layer number 1. This loss is from the transcoder encoder number and layer number 2, layer number 3, etc., and layer number n. And then you can sum up those losses to calculate the total loss. And then this total loss is used while doing the back propagation. This is, however, not done in inference. In inference, let me delete all of this. In inference, you only consider this one. You don't consider all these intermediate layer context vectors. You only consider the last one. So which means you don't have all these losses. You only have one loss, which is corresponding to the last context vector. Okay. Do we have output of 100 nodes in the class MLP? Yes, of course. Because when you say 100 nodes, you mean these 100 object queries, right? I hope that's what you mean. 100 object queries. Yes. So yes, if there are 100 object queries, you will have finally 100 predictions. And for those 100 predictions, you have to construct 100 losses. But how will you construct 100 loss if you have only 5 ground truth? If you have 5 ground truth, you will have 5 ground truth and 95 null objects. For null objects, there are no losses. For 5 ground truth, there will be loss. So that will be the total loss. And the total loss will be used for training. So now let's get back. I want to do one implementation, but let's zoom out and go through the architecture once more. So this is the architecture. Just to reiterate, image feature extraction through backbone CNN. The extracted features are converted to tokens in the embedding dimensional space, and that is passed through transformer encoder. Transformer encoder has a bunch of transformer encoder blocks, and those blocks will convert these sequences into context vectors. Then those context vectors are used in transformer decoder, but before that, you initialize the bunch of object queries, which are null vectors. Those object queries will pay attention to each other in a multi-head self-attention block. In that multi-head self-attention, object queries pay attention, and before that, position embedding is added. For object queries, the position embedding is, which one was it? Was it learnable embedding or was it sinusoidal for object queries? For object queries, it was learnable because object queries do not have any inherent position information. But the 2D feature map is 2D. There was an inherent position information, which means we could construct a sinusoidal function, which acts like something that increases along the row, something that increases along the column, etc. So for these context vectors, in every single transformer encoder, the sinusoidal position embedding was added. Now, this is the in the transformer. Let me go through this diagram. So this is the transformer encoder decoder part where object queries are paying attention to each other. But then these object queries, once it passes through the self-attention, it should now pay attention to output from the transformer encoder, which are context vectors. Now, those context vectors are converted to query and key and value. Query is originating from the object queries. So this is called cross attention because the sequence that produce the query and sequence that produce the key and value are different. So this is called cross attention. But here, the position embedding corresponding to this object queries was learnable position embedding. Position embedding corresponding to the context vectors were sinusoidal position embedding. Okay, so that difference is there. And then cross attention converts these object queries into even better context vector. So now this context vector is rich in information, not just about whatever information it has to communicate between each other, but also about the information about the feature map, which came from the image. Now these context vectors can be converted into object bounding boxes and classes. And for that, we use feed-forward neural network, which has two MLPs, MLP for class and MLP for bounding box, B box. And if there are 4 object queries, there will be 4 boxes that are predicted. And for constructing the loss, we have to map these boxes into ground truth. If we have only 2 ground truth, and if there are 4 predictions for remaining 2 ones, because we need a square matrix for the Hungarian matching. So for the remaining 2 ground truth, we add null objects. So then we map, we construct the loss using detection transformer loss. For every prediction, we try to construct the loss with every ground truth. And there are 3 components for the loss. The first component was the object classification loss, which is due to making a wrong classification prediction. Second component was due to localization. Localization is subdivided into 2 parts. One is L1 loss. L1 loss is absolute losses between prediction and ground truth for the the bounding box center coordinates and the bounding box height and width. The global generalized IOU loss is a better version of IOU loss, which considers the distance between the predicted rectangles also. So using these 3, we can construct the detection transformer loss between every single prediction and ground truth. But then every single prediction and ground truth are not, one ground truth has 1 prediction. And how do you know which one is that? You use the Hungarian matching finally. So then you can use the final loss to perform the backpropagation. In training, for calculating the final loss, you're also considering predictions made by not just the last output of the transformer decoder, but also the in-between intermediate outputs. They are also taken to construct losses due to the first layer, second layer, third layer, etc. And then those losses are aggregated for the total loss. During inference, that is not done. Only the prediction taken from the last layer is considered. Okay. How many of the 100 object query tokens goes into class MLP into the box MLP? Every single one. Every single 100 object query context vectors corresponding to object query will go through the class MLP and box MLP. Because finally, if there are 100 queries, we need to make 100 predictions. What are the predictions? The class and the box. So if you have 100, the reason why you started with 100 query is to predict 100 boxes. Now, not all boxes will be having an object. A very low confidence boxes will be no object, null object. They will be mapped to null object from the ground truth. Now let's do one thing. Let's do a quick, not implementation, inference, because implementation will take very long time, but inference is very quick. So I'll first share the code with you. This is very, very easy. Okay, so you can use this code. This is just for performing inference on a single image, okay? So I'll just run the code to show you how simple it is. Let me, so the code is, I am using a pre-trained detection transformer with ResNet 50 backbone from Facebook. So I'm just directly downloading this from PyTorch. And I have just uploaded some random screenshot. Actually, I can do it. Let me do something like this. So let's say this is my image and I want to run my inference on this image. So just take a screenshot, then upload it here. During the inference, there will be no ground truth. Ground truth, of course. Yeah, correct. Okay, it's not getting uploaded. Let me do once more. Okay, so this is my uploaded image. It's a bunch of dots. Then click on the three dots, copy path, and paste it here because this is a different image. And now I just need to run this. It may install some of the missing packages, but it's mostly fast. This code is very fast. So here, after running the inference, we are just writing these extra parts to, using OpenCV, display the bounding box because we need to draw the bounding box on top of the image. So that's the only reason I'm running these parts. But I just want to show you the output. I think this will run pretty fast. Yeah, so this was fast and this is the output. So it has drawn a bunch of bounding boxes and the confidence score is very high. I'm sure this is like, round off confidence score. It's not 1.00, maybe it's 0.99 and something. And interesting thing is, see here, this bench also is recognized. We can specify which classes need to be identified. So it will specifically identify those classes. Here, I don't know why tree is not identified. Maybe this is a pre-trained on Coco dataset. I'm sure tree is part of Coco dataset, but I don't know why it's not getting identified. Maybe we can do something else, street. Or people. So now let's see if we put this, whether something will work. Yeah, so you see now everything is getting detected. So we can also specify which objects we need to detect. If you don't want to detect traffic light, if you only want to detect person, it's possible. But the original Coco dataset, if I remember, has only 80 classes. It does not have more than that. So every single object in the world cannot be detected. But bus is getting detected with very high confidence, bicycle. So it's very, very good. So just try out this code. It's fairly easy to run the inference. Even in the paper, they say inference can be run in like 50 lines of code or something. Somewhere they mention in the paper. I do plan to put a paper reading video for this particular detection transformer paper. Is the input resolution dynamic? Yes, input resolution is dynamic. Inference, no GPU is needed for this because it's a lightweight model. I don't think it's more than few million parameters. I haven't calculated it, but my feeling is it's not that big of a model. I want to show you one more thing. This code might be slightly slower, but this is equally interesting. This is for video. So you can run the inference on just like how you do on images. You can run it on different frames and you can display the output of those frames. So let me just reconnect here. And I have a bunch of stock videos here like this. So I'll share one video with you, which you can also use. Yeah, I guess this one. So I'm just pasting a stock video on your chat. So just find the video from there. This code, let me share with you. It's mostly the same. I mean, there is no difference. It's just that for annotation, printing the annotated frames and then downloading the whole uh, frames as one single video, you just need to do something. That's all. But that part is very easy. And I'll just show you while this code is running, how the output look like. So original video was something like this, a person walking and then slipping and falling. Can you see the video actually, by the way? I'm not sure if you can see my screen. What all things from my screen can you see? Can you see the screen? Did you see the video of the person falling? Just to confirm if you did not. Okay, okay. Did you you saw the Google Colab code, right? I just want to make sure that can see the notebook. Okay, sure. Let me reshare the screen once. Okay, how about now? Can you see a bunch of things? Can you see this video? Okay, awesome. So this is the video. So I'm running the inference code, which should not take any time to get finished. But because this video has few frames, it will take more time than the other one. But I'll show you the annotated video. So this was the output annotated. So it has annotated bunch of objects that it detected. So it's pretty cool. So that is, yeah, and this code also has finished. So you can basically copy paste any video and then the annotated video you can download from here. So it's very cool. One thing you should definitely try is asking the model only to output certain classes, not every single class. I am currently printing every single class, which is why the videos are looking very ugly. But I want to show you some videos that I have worked with in the past, like some of these. When you annotate, it's very cool actually. So this was not using detection transformer, by the way. This was using YOLO and other models, but it's very cool actually once you annotate specific. So here people are not getting annotated, only vehicles are annotated. Then here, this is on a conveyor belt with bottles. You can annotate and count the bottles. This can be actually done using detection transformer, but we'll have to use some faster models of detection transformer for getting real-time output. This is another cool one, which was again using not detection transformer. This was also using YOLO, but you see the idea. This can be exact same thing can be implemented using detection transformer also. There was one more. Yeah, this is detection plus poster annotation using MediaPipe, Google MediaPipe. So there are a lot of things that we can do with object detection in general. It's like a very interesting area of, there is a lot of industry interest. Oh, did you not see the video which played the basketball video? Did any of you see? I just want to make sure. Okay, awesome. And did you see the what was the second video? The football something that also you saw, right? Okay, awesome. All right, guys. So just try running this code. The inferencing on image is very fast. Inference on video, I'm sure may take maybe 1 minute, 2 minutes. I shared the code in the chat, right? Did I not? Okay, I'll share this. Yeah, this week there will be. I'm yet to post a swing transformer assignment. I deliberately did not post it last week so that there could be a big break. But I'll post it this week. Then videos, I don't have any link because I downloaded it. I can share some videos when I'm posting the assignment. I can share some videos there, so you can take that. But otherwise, I'll tell you some places to get the videos from. Stock videos can be found from Pexels. That is one way. And just for educational purposes, you can just take the videos from YouTube. Like you can download it from YouTube itself. Collab notebook link for DETR, I posted it. Yeah, these are the links. The two links I had posted. For Q&A post link, I don't have it handy right now, but I can post it on Discord. I'm sure somebody has it sampled into frames. And then, yes. So video gets sampled into frames, and frame by frame is how this works. So you might have seen that real-time detection models have frames per second, like number of frames you can process per second for YOLO and all is like 150. For some faster models, it's like 300. Even I have seen models with 500. So if frames per second is 30 or more, then you can call it as a real-time detection model almost. The vanilla version of the detection transformer is definitely not above 30 frames per second, which means it is slower than real-time. But there are other versions which are faster. So in assignment, I think maybe I'll ask you to do inference using one of those models. But it's an interesting architecture, detection transformer, because it's not that different from all the other things that we have learned. It's just that there are a few, Hungarian laws is maybe the only completely different thing. Position embedding is slightly finicky, but other than these two things, I don't think there is anything specially difficult in detection transformer. Swing transformer was different; it had so many different things. Detection, I think it's an okay model. It's not a difficult model. Coding also will not be that difficult in my opinion, because you have repeating modules. You can just easily write that. Hungarian laws has already predefined functions, so we don't want to reinvent that from scratch. But training is a pain. It has to. In the paper also they mentioned that the compute required for training is a little bit longer. But I'll see if I can find a very poor quality data set, like small subset of data set from somewhere where I don't use, because first of all, I don't want to use pre-trained model. I want to use train from scratch, but I can't train on Coco dataset because that is a bit bigger dataset. Then I was trying with RoboFlow, some custom datasets from RoboFlow, smaller, like 100 images, 500 images. Still, the accuracy was very bad. So let's see if something, because if you don't see any good bounding in a box rectangle, it's very disappointing. After, if it's classification, it's okay, you get some prediction, but if you always get no object prediction due to your model being very bad, it's very disappointing. But we'll see. I'll communicate with you. But anyways, thank you so much for listening. We'll meet again next week and try out the assignments. I'll post the assignments by Monday. So thank you so much. See you next week. Bye. So we will continue where we left off in the last lecture. In the last lecture, we understood the architecture of detection transformer. Today, we will be coding a detection transformer almost from scratch. I will tell you why I say almost from scratch. What's the difference? But before we go ahead and code the detection transformer, I want to do a quick recap so that in case you don't remember the architecture, we will just quickly go through the architecture once. So all the models we discussed before detection transformer, vision transformer, data efficient image transformer, and even the code implementation of swing transformer, they were all for classification. We did not do anything for detection, but here is the first time we are implementing something for object detection. So drawing bounding boxes.
So detection transformer, roughly, you can think that it has four parts. Part one is a ResNet 50 or ResNet 18 backbone. So it will be a pre-trained neural network. And this ResNet will extract features from your image. So feature map will have multiple channels. So it won't be RGB. It will have multiple channels in the Z stack, but its spatial dimension might be much smaller than the input image. Input image will simply have three channels, RGB. Once the feature map is available, feature map is projected, flattened and projected into the dimensionality of the input embeddings. So if the dimensionality of this one is 256 and the channel number of channels here are 64, you will have to project from 64 dimensional space to 256 dimensions. But basically what you will do is you will construct a sequence of these feature map in as sequence of input tokens. Then those tokens are passed just like how we pass tokens into a transformer architecture in text. Here we pass it through the transformer encoder, and we had gone into the details of the encoder. Encoder will involve something like this. Something like this. There will be layer normalization followed by multi-head attention. There is residual connection. Then again, layer normalization, multi-layer perceptron, and residual. So same architecture. The only nuance was there in the position embedding. I don't want to go into the details of position encoding or position embedding right now, that we have discussed in detail in the last lecture. But in today's implementation, we will simplify it a little bit so that the implementation is slightly easier. The second aspect is once we have the context vectors from the transformer encoder, these context vectors, the number of these context vectors are same as the number of these input tokens in the sequence. So if there are, let's say, 300 individual feature map grid cells that we extracted from the image, you will have 300 tokens in the sequence. Then we move on to part 3 of the detection transformer, which is a transformer decoder. So decoder will have, vaguely speaking, two types of inputs. One set of input is a sequence called object queries. The number of object queries should be equal to the total number of, or the maximum number of rectangles, bounding rectangles that we want to predict. So if the maximum number of rectangles we are interested in predicting is 4, we simply need 4 object queries. So the number of object queries and number of tokens in your token sequence from the context vectors, they need not be the same. In detection transformer paper, they kept the total number of object queries as 100. So that maximum 100 objects you can predict. So first, a self-attention is constructed where these object queries themselves are projected into query key value space. So that was shown in this image. So first a self-attention is constructed. Let me delete a few things from this. So for this self-attention is constructed so that you can create attention maps between tokens within the object queries. So here query key values are produced from the object queries themselves. But for cross attention, query is produced from the object queries, but key and value are produced from the context vectors resulting from the transformer encoder output. And then same thing, you have layer normalization followed by multi-layer perceptron. So at the end of this transformer decoder, what you get is, and by the way, there are multiple transformer decoder blocks in the transformer decoder and multiple transformer encoder blocks in the transformer encoder. So there are different number of blocks. So we have to explicitly mention how many blocks do we have. Within each block, we have to explicitly mention how many number of heads are there in the multi-head attention, etc. So speaking about the self-attention part here, the reason why it was called as self-attention was because the object queries projected into query key value space, they were those sequence which resulted in producing the query was the same sequence which resulted in producing the keys. So that's why it's called self-attention. Here it's called cross-attention because the sequence which resulted in producing the queries and sequence which resulted in producing the keys are two different sequences. Queries were produced from the object query sequence. Keys were produced from the context vector sequence. Context vector sequence came from the transformer encoder output. So that's why this is called cross attention, because the two different sequences are paying attention to each other. But at the end of all of this, what results is a set of context vectors. And just to refresh your memory, can you comment in the chat how many context vectors will we have? at the end. The number of context vectors will be equal to what? At the end of transformer decoder. It should be equal to 100, or it should be equal to total number of object queries. It should not be equal to total number of input sequence from the feature map, right? It's dependent on total object queries. And then these context vectors are now converted into class prediction or bounding box prediction. So that is what's shown here. So the object queries converted into context vectors can be used, can be fed through two different multi-layer perceptrons. One multi-layer perceptron for predicting the class and probability score. One multi-layer perceptron for predicting where exactly should the bounding box be. So totally, if there are 4 object queries, maximum number of bounding boxes we can expect is 4. So each bounding box is characterized by 4 parameters, the centroid x and y coordinate, the width and height. Everything will be normalized. So all the numbers will be between 0 and 1. Now, sometimes it may so happen that some boxes predict no object. In that case, in a detection transformer, they also define something called as null object, phi. So it's not the case that every single box that the detection transformer predict is mapped into a ground truth box inside the image. Some boxes will be mapped to the ground truth boxes during training, but some boxes will have such low confidence score that it is mapped to it is mapped to null object. And we also discussed something about this mapping, because if the ground truth has, let's say, 5 boxes, and if you are predicting 7 boxes because of your 7 object queries, for example, how do you map 7 boxes to 5 ground truth boxes? You will say you have 5 ground truth boxes plus 2 null boxes. So you have total 7 boxes in the ground truth. You have 7 boxes in the prediction. You try to create the mapping between those two using what algorithm? We had discussed one specific algorithm in the last lecture, if you can mention. How do you match? We match using the Hungarian matching. In Hungarian matching, we discussed about how, using an example, how you can create an optimum score. So the example that we picked was this. There were 4 people who were looking for jobs. There were 4 jobs available. And I am a contractor. I want to distribute the jobs to these workers such that my cost is minimized. Now, each worker proposes different cost for different job, and one worker can only work in one job. So this is where Hungarian matching comes into picture, where I want to optimize the cost. So same thing applies here. So you have predicted boxes, you have bunch of predicted boxes, and you have bunch of ground truth boxes, and you have to construct some sort of, let's say, some sort of loss or some sort of score such that you have to identify the matching between ground truth and predicted boxes to minimize the total loss score. We also discussed about the loss function used in detection transformer. The loss function had 3 components. Let me delete this so that I'm cleaning up this a little bit. The 3 components were, in fact, 2 components. If you look at it from a broader overview. So detection transformer loss consists of loss happening due to classification error and loss happening due to localization error. Loss due to classification error is when I say a dog is a cat. That is an error due to wrong classification. Loss happening due to localization issue is when you say that I have a dog and here is the location, but you are predicting the location wrong. You are not having the closest bounding box predictions compared to where the ground truth box is. So there will be localization loss, and there itself we discussed about 2 losses, L1 loss and global generalized IOU loss. L1 loss was simply modulus of predicted width minus actual width, the plus modulus of predicted height minus actual height, plus modulus of predicted x minus actual x, which is a centroid, plus modulus of y cap minus y, which is the y coordinate of the centroid. This was the L1 loss. And generalized IOU loss was done to prevent something like this. So we discussed 2 cases, and case 1 and case 2. So let's say you have ground truth box like this and prediction like this, and ground truth like this and prediction like this. In both cases, intersection over union, the vanilla IOU parameter is 0, because intersection area between the ground truth and prediction is 0 in both cases. However, we know that case 1 is better than case 2, because in case 1, at least even in IOU being 0, the boxes are slightly close to each other. In case 2, they are very far from each other. So this is where we constructed something called generalized IOU, where we said we will draw another box, which is the smallest box that encloses both of these boxes. And based on this, we can construct a formula like generalized IOU equal to IOU minus 1 plus P union G, which is prediction union ground truth divided by C. C is the big rectangle which encloses both of these boxes. And based on this formula, we can construct generalized IOU. And we also discuss why the generalized IOU for this case is better than this case, right? So this is where and then we also implemented a simple inferencing on a detection transformer, pre-trained detection transformer we downloaded from Facebook. So this is where we ended last lecture. Now, what we are going to do today is something simple. I had mentioned in the last lecture that training the detection transformer from scratch is difficult. So that is still true. If you read the detection transformer paper, you will realize that training requires a lot of time. But what we are going to do is we'll simplify everything. We will define the detection transformer from scratch, but we will not train it from scratch, but rather we will import pre-trained weights from Facebook so that we will get the experience of coding it, but we will not experience the pain of having to train it for a long number of hours. So within the lecture duration itself, we can try implementing the detection transformer that we coded with pre-trained weights. Now, one thing you have to note here is the pre-trained weights are being imported with certain variable names. So you should follow the exact same variable names for your code to work. So when you are coding along with me, I would like it if you are using the exact same variable names, because the pre-trained model has certain parameter names and we don't want to change that. So now what we can do is we can open a Google Colab notebook, empty notebook, and we can start coding. So please get ready with your Google Colab notebook. So there are a bunch of things that first we have to define. As always, we have to define imports. Then we have to define a detection transformer class for defining the whole detection transformer. And detection transformer is actually easy because if you think about it, there is just there is just ResNet backbone, transformer encoder, transformer decoder. The parts that may be tricky will be position encoding that we will simplify. And here, in fact, we don't have to. Okay, there is a question: how will we know the parameters of pre-trained model? We can print it if we want to, but the parameters we are importing from a saving point which is available from Facebook. So, but if you want to see the parameters, we can. I think there are options to print it. But basically, those number of parameters will be very high, right? The question is, what are the variable names of the pre-trained model? That also we can know from the documentation of Facebook. Okay, so first we will define imports. Then we will define a class for writing the detection transformer. Then we will need a code block for loading pre-trained weights. Then we will load the Coco dataset classes because the pre-training has happened on Coco dataset. So if there are 91 or something classes, we will load Coco dataset classes plus some colors that we can use while drawing the bounding box. So colors for bounding box. And we need a function. We need to define a function for scaling the B box coordinates, because the by default the predicted bounding box coordinates will be between 0 to 1, but we can't use 0 to 1 because we need to finally show the bounding box inside our image, and image has certain dimensions, width and height. So we have to scale this from 0 to 1 to WH scale, right? So that for that we'll need a function. Then we will need another function for predicting the function, or another block rather, for predicting the output or outputs for a given input image. And how do we get the input image in the first place? We will need another block of code for defining the input image, and then finally plotting the results. Basically, what does this mean? Overlaying image plus bounding box plus predicted class plus confidence score. So these are the 4 things that we'll display. So now we have to write these many things. I'll do one thing. I will share the link to this collab notebook so that you can write it yourself. But if in case if you face any issue, you can refer to my code directly. All right, so let's start with the imports. So as always, we import Torch, PyTorch, import Torch, then import matplotlib.pyplot as PLT for plotting images. Then from below, we import image. This is for reading images. Then from Torch, import NN so that we can use NN.module. Then we should also import the ResNet 50 or any ResNet architecture. So the backbone that we are going to use today is ResNet 50. So from Torch vision.models, import ResNet 50. So this is what we will define as the backbone. Then import Torch vision.transforms as T. We were using this to perform certain transformations like from pillow format into tensor format and so on. And import requests, this we will need later. And that's it. I don't think. And one more thing which we can do is, since we are not training the model here, we are only defining and loading the pre-trained models. We can speed up the whole code by not storing any gradients. Like so we can simply set PyTorch to not store any gradients. So set grad enabled false. We can try without this line also, but let's keep it for now. So these are all the imports. So let me just add a text saying imports. Then just run the block of code to make sure there is no syntax issue or some minor issues which you are overlooking. Now we will code probably the difficult part. The difficult part is coding the detection transformer class. So, okay, there is some issue here. Cannot import image from PIL. From PIL import image because this should be capital letter. Thank you. Yeah, because gradients we will need. The reason why we are not storing gradients is we are not performing training here, because if we were to do training, it's very slow because detection transformer requires very long training schedules. So in this case, we are only using the model. We are defining the model. We are using pre-trained weights, and then we are directly using it for inferencing. We are not fine-tuning also. If we were also doing fine-tuning, we will not set this to be false. Okay. So here it's pure inferencing, but still we are writing it from scratch. So we get the best of both worlds. We get the experience of writing the model from scratch, but we don't wait long number of hours for the training to finish. Now we will write detection transformer class definition. Okay, so now let's start with class DETR. We can call it as demo class because we are just, this is not the exact original detection transformer class. There are a few differences with respect to position embedding, etc. And here we will require nn.module so that we inherit properties from the nn.module parent class. Then define underscore init. We define the init constructor, and we have to pass a bunch of parameters here. Of course, one of the most common parameters is self. Rest we will write in a moment. We also have to call the init constructor from our parent. So super dot underscore init underscore for the initiation of the init, for calling the init constructor of the parent class. Here we should pass a bunch of things. So first is number of classes. Whatever is the number of classes in Coco, we should pass that here. I think it was 91. So we can just pass it here itself. So our model, our object detection model, will be able to detect those objects belonging to one of these 91 categories. It won't be able to predict any other new classes. Then whatever is the hidden dimension, so hidden dimension, we will keep it 256. So for us to be consistent with the implementation of this particular pre-trained model that we are writing. So this is the hidden dimension in the encoder as well as in the decoder. So hidden dimension of the sequence of tokens in encoder, hidden dimension of sequence of context vectors in encoder, as well as the object queries in encoder. Then number of attention heads, n heads, equal to 8 as per the implementation of pre-trained model. So this is the number of heads in the multi-head attention. Then we need to define how many blocks of encoder and how many blocks of decoder are there in the encoder as well as decoder. So blocks meaning how many layers are there in series. These attention heads are actually in parallel. These attention heads are part of a multi-head attention. So every attention head will be 8 attention heads in parallel. But in encoder blocks, in encoder part, there are encoder blocks in series. In the decoder part, there are decoder blocks in series. So we can define that. So number of encoder layers equal to 6. And same for decoder. So we'll say number of decoder layers is also equal to 6. So I think that's all the parameters we have defined here. Now we have to create three things actually. First is ResNet backbone. Then second is defining the transformer with encoder plus decoder. Third is we should have the MLP for class and MLP for bounding box, B box. So these are the three things now we will define. So first, let us start with ResNet. ResNet part is easy. Self.backbone. So backbone is the variable name that we are using. And here we have already imported ResNet 50. So copy this and call the ResNet here. So we are saying our backbone is going to be ResNet 50. Now I have one question here. When we are using ResNet 50 here, is this ResNet 50 pre-trained or not? The one which we just defined. Is it a pre-trained ResNet or is it not a pre-trained ResNet? Okay, all of you are saying it's a pre-trained ResNet. So the ResNet that we just defined is not a pre-trained ResNet. It's just the ResNet architecture. The pre-training will come from the pre-trained weights that we are going to import, right? So when we say we are going to import pre-trained weights of detection transformer, that will include pre-trained weights not just in the encoder and decoder, that will also include the pre-trained weights in the ResNet 50. So here pre-training is not defined. Okay, here it's simply the architecture. Pre-training will be automatically done once we are importing it. So please don't get confused here. So when we define it here, weights are random. So here we just define the backbone structure will resemble that of ResNet 50 architecture. That's all. Okay, and then we have to do one important thing. This ResNet is pre-trained. I mean, this ResNet is supposed to be pre-trained on like 1,000 class classification or something like that. So whatever is the last layer, we have to remove it. So delete, so dil self.backbone dot last fully connected layer, because last layer is meant for classification. Here, we are not using ResNet for classification. We are using ResNet just for extracting features. So we can simply remove the last fully connected layer with this line. And then we have to project whatever output we get from ResNet into. So if we go back to our diagram, so this is our diagram. So this ResNet will extract a feature map of certain dimensionality or of certain channel size. We have to project that into 256 dimensions, because here we have defined our embedding dimension to be 256. Where did we define? We defined it over here. So we have to project whatever is the output number of channels coming from our ResNet backbone into 256 dimensions. So the ResNet backbone output dimension here in this particular case happened to be 2048. So we can define a nn.con 2D operation. So nn.con 2D, where this con 2D operation projects from a 2048 channel output at the feature extraction. So ResNet features are extracted such that there are 2048 channels. And this is being projected to hidden underscore dimension using a kernel of size 1 by 1. So we are simply doing a projection using a nn.con2d. Usually whatever follows nn.con2d, as we have discussed in this lecture series many times, will be learnable parameter. But this, in the current case, it's not a learnable parameter because we are not going to train on top of it. But initially when we define it, it will appear like a learnable parameter. So here we define the backbone, we remove the last fully connected layer, and then we project whatever output we get from the ResNet, which is in 2048 channels, into 256 dimensions. Then, so now ResNet is done. That's it. So basically, ResNet backbone is very simple. Okay, there are a couple of questions. We are using ResNet for converting input image to tokens. Why can we not use conv operations that we have done in the... we are not using ResNet to convert input image. Okay, so ResNet backbone is required because if we directly convert image into tokens, we will be doing what? We will be using patches. Then it will not look like a detection transformer. It will look more like a vision transformer. So detection transformer, one of the best things that they did was they did not shy away from using convolution operation, right? So if we did not use convolution, if we just divided the image into patches and then converted those patches into tokens, we will lose the awesome feature extraction ability that convolution operation brings. So convolution operation is needed here because the filters that are used in convolution has a much higher power of extracting features. And once those features are extracted, use those features to create the tokens instead of using image directly to create the token. So that's the difference between detection transformer and vision transformer. I mean, of course, vision transformer does not have a decoder because vision transformer was meant for classification. So that is also another difference. But that's the idea. Okay. So ResNet backbone we define. Then we remove the last fully connected layer, which was meant for classification. And the layer before that will output something at 2048 channel dimension. And but we don't need 2048 channels. This projection would have been unnecessary if our hidden dimension was also 2048, our input embedding dimension. But input embedding dimension happened to be 256. So you project from 2048 to 256 using nn.con2d. Here one is the patch size. Now, so that's it. It's easy to define. Now, you may think that transformer part is the most difficult part to define. In fact, it's the easiest in this case because we are not going to define transformer blocks from scratch. Here we can leverage PyTorch. So we'll say self.transformer. This is literally one line equal to nn.transformer. So previously, if you remember, we did not write nn.transformer in any of the architectures. We always wrote nn.multi-head attention. The rest of the things we were writing manually. But here, if we were to write it manually, we'll have to write multi-head attention. We'll have to write nn.sequential so that those, we'll have to write multi-head attention, multi-layer perceptron. We will have to write layer normalization. Then like that, we will define one transformer encoder. Then that encoder we'll have to repeat how many number of times? 6 number of times by using nn.sequential. All of that can be easily avoided by not writing it from scratch. We can use the nn.transformer itself. And this transformer by default, it can accept arguments that define transformer encoder and transformer decoder. We would not have done this if this model only contained a sequence of just one transformer encoder, because then writing the transformer encoder from scratch is easy, just like how we have done in vision transformer or data efficient transformer. So here we will say nn.transformer encoder. So first we have to mention what is a hidden dimension. So hidden dimension we copy paste here. Then we have to mention what is the number of heads in the multi-head attention. Then we have to define what is the number of transformer encoder layers. And then we also have to define how many number of decoder layers are there. So that this is the purpose of these 4 numbers that we define, so that these numbers define our transformer, the whole transformer. When I say whole transformer, I mean both encoder as well as decoder. So now PyTorch will take care of everything that it has to do to define the transformer. That's it, just one line. Now we need 2 lines of code for 2 multi-layer perceptrons, one for predicting the class and probability score, one for predicting the bounding box. So self dot linear classes linear head for classification is nn.linear. And here we will be projecting. So here, what do we get? First of all, what is the input that goes into this MLP for classification? Can anyone mention the input that goes into? And I'm not talking about input dimension. I'm talking about what is the thing that is the input into nn dot that goes into the multi-layer perceptron. It is some output that comes from transformer decoder, correct? What is the output that comes from transformer decoder? Object query is converted into context vectors. What is the dimensionality of object queries? Dimensionality is the same as the hidden dimension. So at the end of the day, my MLP is basically projecting something from hidden dimension into something, right? Can you tell me what is the projection to? How many classes do we have? Because this is for classification. We have total 91 classes, but actually we have total 91 plus one more class for null object. So we said that detection transformer considers null object also. So number of classes plus one. So this plus one is because detection transformer has null object also. Null object for those boxes without high confidence score. And these are 91 classes in the COCO dataset. Okay, so that is where this variable is being used. Now we can also define self dot linear layer for bounding box. So B box equal to, again, nn dot linear. So here, can you tell me, again, input is coming from the transformer decoder output. Transformer decoder output are the context vectors corresponding to object queries. The dimensionality of those context vectors are all 256, which is the hidden dimension. But what should be the output dimension here? We are projecting from 256 dimensions to what? To 4, because every 256 dimensional context vector corresponding to the object query is used for predicting the bounding box. Bounding box has 4 parameters. So here we will go from hidden dimension to 4. Those 4 parameters are centroid xy, width, and height. Okay, so MLP is done. Now we have to define position embedding. So there are 2 parts where we were adding position embedding. One was position embedding corresponding to sequence of features which we extract from the image. Second was there can be multiple B box. So multiple B box will be there, but every single token is projected into 4-dimensional. But like that, there will be 100 tokens. Why? Because object queries are 100. But if you look at it from the perspective of one token is projected into 4 dimensions, right? Now, position embedding needs to be added for 2 sequences. We have 2 sequences here. One sequence is a sequence of feature tokens. Another is the sequence of object query tokens. So we had two types of position embedding used here. So first is, we can say position embedding for object queries. So position embedding for object queries. So this we can call self dot query position embedding, query underscore pos is equal to, this we will define as a random parameter. So random nn dot parameter torch dot random number, and we need 100 random numbers, and each random number will be of what dimension? Each random number will be of hidden dim dimension, because the position embedding vector should be of the same dimensionality as that of the input embedding vector. So, and why 100 here? Can anyone explain why do we mention 100 here? Because there are 100 queries, right? There are total 100 queries, and each query should have separate position. In the actual detection transformer paper, if I remember correctly, it was not initialized as random, it was initialized as zeros, but here we are initializing it as random. That is one difference. Next is position embedding for the image feature sequence. So here there is a little bit of complexity. The complexity is that image feature sequence also we can, define something like self dot feature position or something. We could have called this like this. and then nn dot parameter, torch dot rand. This will be hidden dimension, but this will be, instead of 100, it will be width of the feature matrix multiplied by height of the feature matrix. We could have done something like this, but that will not give us the information about the fact that you actually have XY. It's a spatial, originally it was a spatial feature matrix, right? So features were extracted from image. There was some spatial information. So if we can somehow preserve that spatial information, that'll be great. So we have to create parameters corresponding to row and corresponding to column separately. So what we do is self dot row embed, we will define, then self dot column embed also we will define. Okay. Now row embed, we will say it's also a parameter, and we will start as a random parameter, and the embedding dimension will be hidden dimension divided by 2. I will say why divide by 2, because we are going to concatenate row and column. So that hidden dimension divided by 2 concatenated with another hidden dimension divided by 2, totally it will become hidden dimension only. So here the dimensionality of this row embedding is hidden dimension divided by 2. But what is this? It's actually not 100. What is this 50? And this should be also torch.rand 50 comma. So what is this 50 number? In fact, this can be 50, this can be 100, etc. It can be anything, but what should this number be ideally, according to you? See, what was this? This 100 was the number of positions that we require in our object queries. Because we had 100 object queries, right? We defined 100 position embeddings. By the same logic, if we are creating row embeddings, here this should actually be number of rows, which means width of our feature matrix, right? And this should ideally be, since this is column embedding, this should be height of our feature embeddings. So that is what we want to define, but we don't know the width and height here, where we are defining this, because here this is just a framework. We have to define the forward function to actually know what is the width and what is the height. So what we say is the ResNet 50 model, when it creates this 2048 dimensional or 2048 channel feature matrix, the spatial dimension is something like 42 by 25 or something like that. So any number greater than 42 will work here. So this can be 43 and 43, because later I can say, yes, I am creating 43 row embeddings and 43 column embeddings, but I don't need 43 column embeddings. I only need 42 column embeddings and 25 row embeddings, because the feature matrix that ResNet 50 outputs will have 2048 channels, but height and width of that is 42 by 25, something around that, which means any number greater than that maximum number of width or maximum number of height you need is good enough. So here, to be safe for ResNet, you can define this to be 50. You can define it to be 100. You can define it to be 500. Anything is fine. But we won't be using all of them. We won't be using all the 50 row embeddings. We won't be using all the 50 column embeddings. We will only use that many row embeddings as there are number of rows. So if there are only 42 rows, we'll only use 42 row embeddings. If there are 25 columns, we will only use the first 25 column embeddings, right? So here the reason why we select 50 is because we want to define a number that is greater than the maximum dimensionality, maximum spatial dimensionality of the ResNet output. Now we want to, but still position embedding is not something of hidden dimension divided by 2. It has to be that of hidden dimension. So somehow we have to use the row embedding and column embedding to create our final position embedding. So what we say is that we can do in the forward pass. But just let me just draw and make this clear for you. So if we have a ResNet backbone, from this backbone, we are extracting something. This something has 2048 channels, but this dimension is 42 and 25, something like this. And we are projecting this into a dimensionality of 256. So this will be 256. Okay. But this will still remain 2542. So the total number of tokens that we have in our token sequence of the feature map is only 25 multiplied by 42. But the total number of position embeddings that we have just defined is 50 multiplied by 50. But we don't need this many, but we are defining it to be safe such that we have these many at least token position embeddings available. In the case of position embedding for queries, object queries, we said the number of tokens that we need was 100. The dimensionality of each of those number of position embeddings that we need, vectors that we need was 100. The dimensionality of each of those position embedding vector was 256, which is the embedding dimension. Here also, ideally, we just need 25 by 42. That many, this number, I'm not 100% sure whether this is 25 and 42, but I just know it's less than 50. You can check this. But basically, we just need only these many position embeddings, each with 256 dimensions. That is one requirement. Second requirement is, this should not be just a random sequence. The sequence of these position embeddings should somehow encode the fact that you have rows and columns, because there is a 2D nature to this, right? Because this is two-dimensional information. So that is why we define the row position separately and column position separately, so that we can combine those two information to produce sequences which take into account the fact that there is a 2D information here. So position embedding can somehow embed 2D information. So those are the two requirements. And how are we satisfying this requirement? We are satisfying this requirement by saying that I will define 50 row embeddings and 50 column embeddings. So maximum I'll be 2500 I'll define, which is greater than this number. 2D information I'm satisfying by the fact that I'm defining column embedding and row embedding separately, and then I'm later concatenating. Why do we require concatenation? One reason is we want to mix the row and column information, but at the same time, this is defined to be of hidden dimension by 2. This is also defined to be of hidden dimension by 2. But our actual dimensionality will be 256, which is hidden dimension itself. So when you concatenate this and this, you will get hidden dimension by 2 plus hidden dimension by 2. So total dimensionality of your embedding will be 256. So this is what we are doing. All right. Now we can write the forward pass. Okay. So forward pass is where the model will be passing each token. So define forward. And every forward pass usually had two inputs, self and x, where x is the current token. But here we can call this as inputs, self comma inputs. Then I think my indentation is wrong. Yeah. Then first we have to do forward pass through ResNet. So forward pass through ResNet. So here we use different layers of the ResNet separately. So x equal to self dot backbone. So self dot backbone is the ResNet backbone. We had defined self dot backbone here to be ResNet 50. So x equal to self dot backbone dot the dot conv1. Conv1 is the first convolution happening in the ResNet dot input. So this conv1 is defined just by the fact that we are defining the backbone to be ResNet 50. So conv1 is already defined inside ResNet 50. Then we again pass it through the next ResNet layer, self dot backbone dot batch normalization. So first batch normalization in ResNet. So this is part of ResNet structure. Okay, I'm not pulling this out of nowhere. This convolution, this batch normalization is part of the ResNet structure. X equal to self dot backbone. From the backbone, we pull the ReLU for activation function. Then x equal to self dot backbone dot max pooling. So max pooling will reduce the spatial dimensionality of x. And now, so none of these are ResNet blocks. So ResNet has the blocks called residual blocks. Oh, inputs. Yes, thank you. Residual blocks. So none of these have residuals. This is convolution. This is batch normalization, ReLU, max poolings. And now comes the actual ResNet block. So x equal to self dot backbone dot layer 1. So layer 1 is the first ResNet block. Then x equal to self dot backbone dot layer 2 of x. And like this, we will need layer 3 and layer 4. So 4 residual layers. So ResNet 3 and 4. So by the time why can we not do simply self.backbone of inputs? Because self.backbone, we are not using every single layer in the ResNet. The ResNet 50 will have 50 layers. So we are not necessarily using everything, right? We are only using it according to what this small pre-trained model was trained on. So we want components from the ResNet, but we don't want the whole ResNet necessarily. I think we are making the ResNet model a little bit smaller by doing this than the original ResNet 50 architecture. And that was maybe done by the people who pre-trained this model to make the pre-training a bit fast. Okay. Then we say we had defined one thing here. We had defined a self.convolution. This convolution was done to project the number of channels, which was 2048, into a hidden dimension, right? So now whatever output we have, we can project into our hidden dimension. So now we say h equal to self.conv of x. So by the time of this layer 4, we will have 2048 channel dimension, and this h will not have 2048 channel dimension. This h will have only 256 channel dimension. So this is the forward pass happening through ResNet, and this is projecting from 2048 to 256 dimensions. And now we have to pass this through transformer. But before passing this through transformer, we have to define the position embedding, right? So now let's extract height and width. So height comma width, because we need to know the height and width of the inputs, so that instead of using all the 50 row embedding and all the 50 column embedding, we can just use how many ever we need. So h comma width equal to h comma shape of the last two dimensions. So -2 means last two. So this will extract the height and width of each of the input feature. Then we say position embedding pos equal to torch.cat. So here is where we try to concatenate row embedding and column embedding, but we have to do a little bit of processing. Processing meaning the dimensionality should match. So first, let's write just what we are trying to do. We want to concatenate self.rowEmbed and self.columnEmbed. However, what we have to do is we don't want the whole of this. We just want for row, we just want everything from 0 to W. For column, we just want the position embeddings. We don't want from 0 to 49. We just want 0 to width. Similarly, for column, we don't want, for column, this should be 0 to width. For row, this should be 0 to height. Correct? Another thing is, this one has only, it had only 2 dimensions, basically. Or rather 3, it had only the number of sequence, basically number of images in the sequence. And it had per image width and height, but batch dimension is absent here. So we have to add a batch dimension at position 0. So what we do is we add unsqueeze of 0, which means an extra 0th index item will be added to add the batch dimension. So this will increase the dimensionality of this position, this self.columnEmbed by 1. We have to add that here also. I'll explain this to you once in detail. Let me first write this. And then we have to repeat this position embedding because this is column embedding. So for every single row, as long as the column identity is the same, column embedding can remain the same. Similarly, for every column, as long as row embedding index is same, that value can repeat, right? Because with the row index of 3, maybe there are 6 different columns. With the column index of 5, maybe there are 4 different rows depending on the size of the matrix. So what we can do is we can make this thing repeat a few times. So we do dot repeat of h comma 1 comma 1. So what we are doing here is that this column embedding, we are making it repeat along every single rows. Similarly, a row embedding, we are making it repeat along every single column. So since it is repeated along column 1 comma w comma 1. So what we did here is in this line, we had 50 column embeddings, but we extract only as many column embeddings as there are number of columns, which is the width. Here we extracted those row embeddings. We did not extract everything till 50. We extracted only from 0 to h, because h is the total number of rows, because h is the height. So we don't want all the row embeddings from 0 to 50. Then unsqueeze of 0 will add a bash dimension. Dot repeat of h comma 1 comma 1 will ensure that my column embedding is repeating along every single row. Similarly, dot repeat of 1 comma w comma 1 will ensure that my row embedding is repeated through all the columns. And then torch dot concatenate, meaning this whole thing is concatenated with this along which dimension? We can mention the dimension along the last dimension equal to -1. And what is the last dimension? Last dimension is the embedding dimension. Embedding dimension was originally hidden dimension by 2 for this guy, and hidden dimension by 2 for this. And when we concatenate two such things, the last dimension of this concatenation will become embedding dimension itself. Okay. And then we do one more thing. So now we have a sequence of, I'll explain this to you once I write the code, sequence of token, which we flatten the height and width dimension, and then unsqueeze of 1. So I have written this down because there is a little bit I want to explain. Let me first copy this code and let me go back to my Miro. So let me paste this here. Okay. So this is the code. Okay, so let's now go through this. So what we are using here is this position embedding is added to, okay, actually, let me write one more line of code because I want you to see where the position embedding is added. Then only the position embedding's dimensionality will make sense. Because I hope this part is clear for you, but this you need to see why we are doing this. And for that, I need to write one more line of code. Now, we add the position embedding to the variable h, because h is now the extracted features projected into 256 dimensions. And before we pass this into a transformer, we should add this. So let me write this. H equal to self dot, actually, let me, before passing this, h equal to position embedding plus h dot flatten of 2 dot permute of 201. This also needs explanation, so we can explain both together. So this is one input that goes into the transformer. So the transformer requires two inputs. One is the input corresponding to encoder, and one is input corresponding to decoder, because in the transformer, we are defining both encoder and decoder. So the input that goes into encoder is basically the flattened sequence of tokens in the appropriate order. So this order is, the permutation is done for a specific reason, which I'll explain in a moment. but there are two inputs that go into our entire transformer: input corresponding to encoder, input corresponding to decoder. Input that goes into encoder is nothing but the sequence of features that are converted into 256 dimensional space, which is also flattened. But to those features, we are adding the position embedding. So position plus h dot flatten of 2 dot permute of 201, that is one input. Another input that goes into our transformer, not in encoder, but in decoder, is the position embedding corresponding to, is the object queries themselves. So self dot query position dot unsqueeze of 2 of 1 dot, then here we have to call self dot transformer and then dot transpose of 0, 1. So few things I have to explain here. I have to explain why this transpose is done. I have to explain why this unsqueeze is done. I have to also explain where exactly is the position object. I mean, where exactly is the object queries, because we defined the position embedding for object queries, but where exactly is the object queries themselves. So what we can do is we can simply say that the position embedding corresponding to object query is this. I mean, the object queries are the position embeddings themselves, meaning object queries were, if you remember, in original detection transformer started as 0 vectors. To those 0 vectors, we added learnable position embedding, if you remember. So when you add a 0 vector with a learnable position embedding, effectively that vector is learnable, the learnable position embedding itself, right? So this query position embedding is a learnable parameter. You have 100 such learnable parameters, each of 256 dimension. If you add these 100 vectors to another set of 100 0 vectors, the result is this vector itself. So you just need one vector to start with for the object queries. So here into the transformer, we are passing two inputs. The first input is the input that is supposed to go into the encoder block. Second input is the input that is supposed to go into the decoder block. So decoder input is the object queries themselves, which is equal to, numerically equal to the object query positions. Here they are learnable embeddings. In the actual transformer, in the actual detection transformer, these were actually sinusoidal position embeddings. The position embeddings corresponding to the sequence of object features, they were sinusoidal position embeddings, if you remember the discussion from the last lecture. But here we did not use sinusoidal position embedding. We used a row and column position based position embedding. That's one difference. So we are adding the position embedding to whatever output we get from projecting our 2048 channel output from the ResNet into 256 dimensions. So we are adding position embedding to this. I'm yet to explain these dimensionalities. I'll come to that in a moment. But overall, I hope you understand what this parameter is. Here, effectively, this is the position embedding added with the object query, which is what we are passing into the transformer. And whatever output we get from the transformer, we are transposing for a certain reason. So now with this understanding, now with the fact that this is the line that we are looking at, we can try to go through the reasoning behind, the Python reasoning behind why are we doing this permute operation and transpose operation. There is nothing conceptual there. It's just due to the reason of how Python is representing a few things. So how do I start? Okay, let me start from here. So look at this line of code. In this line of code, we are adding position embedding with h dot flatten of 2 dot permute of 201, which means obviously the dimensionality of this and the dimensionality of this should be the same. So once we understand why the dimension, what are we doing with this h variable, once we understand that first, then we can go back to what we were doing with this position embedding dimensionality. Why were we doing some certain operations that we will easily understand. So first, let us look at this h dot flatten of 2 dot permute of 201. So firstly, what is h? H is the output that we got after we performed this conv operation, we did convolution operation to project our channel dimension from 2048 to 256. Now we have to first ask initially, what is the dimensionality of this H? The dimensionality of this H is, it has 4 dimensions. First of all, it's a tensor. So H will have a batch dimension, channels, height, and width. So here, if the batch size is 1, number of channels might be 256 because we have transformed. Height will be 25 or 42 or something. So let's keep this 25 and width is 42, something like this, right? So this will be the dimensionality of the variable H. It has 4 items and batch, channels, height, width. Now, when we do the flatten of 2, what we are doing is we are combining the height and width into one single thing, because finally, when we are flattening the whole sequence, we are not keeping the 2D structure. The features which were extracted in 2D should be finally flattened before passing into transformer encoder. See this. This was in 2D. So if this was H and if this was W, H times W, that is the total number of tokens in this sequence here. So we have to combine H and W, which is what we are doing here. So first we say flatten of 2 means everything after second dimension will be combined. So this is 0th dimension. This is first dimension. Second dimension is height. Third dimension is width. So second and third dimension will be combined. So now H will become something like this. Batch, channels, then width times height. What is width times height? That is the total number of tokens in our input sequence. So that is H dot flatten of 2. Now we do a permute of 201. So permute of 201 means this is 2, this is 1, this is 0. 2 will go here. 0 will go here. 1 will go here. So now the dimensionality will become height times width, comma batch, comma channels. Now look at what this is. Height times width is number of items in the sequence or sequence length. Batch is basically the batch size. Okay, this part is understood. Channels is the embedding dimension. Now, you might naturally have a confusion that isn't usually batch dimension the 0th dimension? Isn't that what we are supposed to do? So why are we doing dot permute of 201 instead of permute of 0 to 1? Something like, because 2 and 1 should be replaced, or basically transpose of this last dimension and second last dimension. Why are we keeping batch dimension as the dimension number 1 and 0th dimension as the total number of items in the sequence? The reason why this is done is actually in PyTorch transformers, it expects this kind of a structure. You might remember from the vision transformer lecture where we implemented MNIS that when we were defining the multi-head attention, if we did not have this batch first equal to true, if this was not there, we were getting very poor accuracy. That was because by default, there our data set was in such a way that batch was the first dimension. So we had to explicitly tell PyTorch that our first dimension was batch. But if this statement was missing as an argument in the multi-head attention, we were getting wrong responses because PyTorch will by default expect sequence length to be the 0th dimension. So here we are passing sequence length as the 0th dimension. So now let's look at what is the dimensionality of this at the end of the day. This H dot flatten dot this thing. It will be sequence length, comma, batch, comma, embedding dimension. This is how this looks like, which means if we are adding another vector like position embedding, it should fit this. Now let's see what we are doing with position embedding. Position embedding was this. Let me copy paste it here. I think I have already done. So first step, I hope you already understood. Self dot column embedding of column W. Here we are extracting, instead of all the 50 items, we are only extracting things until W. And okay, so here let's read this. You have a feature map H of shape batch, comma hidden dimension, comma H, comma W, and which we are converting it into a certain shape. I think this part we are already knowing, I think. But we want to know why we are doing this flatten of 0, 1 and dot unsqueezed of 0. So here the dimensionality of this self dot column embedding will be h comma 1 comma 1, I think, and dimensionality of this will be 1 comma w comma 1, and this 1 is basically the embedding dimension. So finally, when we concatenate these two, it will look like h comma w comma embedding dimension. So before we do this dot flatten of 0 comma 1 and dot unsqueeze of 1, I think the dimensionality, if I'm not wrong, should look something like this. Let me check if there is any mistake. Dot unsqueeze of 0, h comma 1 comma 1, dot unsqueeze of 0. Last dimension is embedding dimension. Then flatten of 0 comma 1. Yeah. And now when we flatten 0 comma 1, this will look like these two items will be combined into one single thing. So h times w comma embedding dimension. This is what will happen after the flatten of 0 comma 1. Then after of unsqueeze of 1, one additional dimension will be added, h times w comma additional dimension will be added here, comma embedding dimension. And here batch size, this is basically the batch size, right? So now if you, and this is what, this is the position embedding variable. If you now compare the position embedding variable, h times w is what actually? This is the sequence length, the total number of tokens in our sequence. The second dimension is the batch dimension. Last dimension is embedding dimension. And this one also was expecting something like that. Sequence length, batch size, embedding dimension. So this is the kind of the Python logic why we are performing these operations. But the basic logic, the basic idea is simply the same. You add position embedding to the token sequence before you pass it to transformer encoder. Into the transformer, you pass both the input into the encoder as well as input into the decoder. Okay. So now we will, after this h will transform to whatever output comes out of the transformer decoder, because this transformer is a sequence of encoder and decoder. Now what we can do is we can say return. I don't think we have defined this thing yet. We said we will define the multi-layer perceptron. Okay, this we are yet to use, but let's come to that in a moment. Now we can return two things. Predicted logits why we take transpose. Oh, yes, great question. I forgot to mention that. So the reason why we take transpose is the transformer encoder output, transformer decoder output will be in this format. Sequence length, batch length, embedding dimension. But in general, for training, for plotting everything, the easiest thing for us once we are outside the transformer, as usual for any tensor, is to have batch here and sequence here. So for that reason, whatever output we get from the transformer, we flip the 0th dimension and first dimension. We transpose the 0th and first dimension so that batch comes back to the 0th dimension once again. So that is what this line does. Dot transpose of 0, 1 means finally this h, after we have the output. So this is now the transformer output. That output we transpose such that batch dimension again comes back to 0, so that late in training, in plotting individual images, etc., we are usually used to batch dimension being first. So we don't have to change the code anywhere else. This is just to take care, this whole exercise is just to take care of the fact that transformer was defined in such a way that sequence length was the 0th dimension. Okay. And here we have to output the predicted logits, and one more thing we have to output is predicted boxes, bounding boxes. So two things we have to output. And how do we output this? Logits are nothing but h converted into something using this linear class. So self.linear class of h. Then, and here also, like in this linear class multi-layer perceptron, it expects batch dimension as the first dimension. Then this will be self.linear box or b box. I forgot the, yeah, linear b box. Self.linear b box of h, but then bounding box coordinates should always be between 0 and 1. So the simple thing which we can do to ensure that this number is between 0 and 1 is pass it through a sigmoid function, so that it will be between 0 and 1. And that's it. There is a question: is the sequence length the data set it needs to give output through weighting of vectors, and is sequence length the data set it needs to give output through weighting of vectors? I'm not understanding the question actually. Could you rephrase it? Are you asking what is the sequence length? If that is the question, sequence length is simply the number of tokens. Number of tokens is basically total number of height multiplied by width of the feature, the feature matrix. Feature matrix has 2048 dimension, but certain height and width. Height multiplied by width is the total, is the sequence length. Features, the channels were 2048, which we project into 256 dimensions. So we implemented three things here in the forward pass through ResNet. Then this was forward pass through the transformer. Let me write it here. Then in the return, there was a forward pass through the MLPs for classification and B-box prediction. So that's all. I think we coded the most difficult part in today's lecture. This is the detection transformer. Let's run to see if there is any basic syntax issue or not. I think it's fine. Okay, so now it's relatively simple from here. So first is using pre-trained weights or importing pre-trained weights from Facebook. This line of code, it requires a particular URL, but I'll write everything except that URL. I'll just copy paste. So DETR equal to this name, whatever the name was, DETR demo, and nothing we need to pass here. And then state dictionary. This is where we import something from PyTorch. So torch.hub.load state dictionary using URL from _URL. And this is where we have to pass the URL equal to something. And that's all, just URL equal to something. We'll put the URL in a bit. Then once we have this detection transformer dot load _state dictionary of, and then we pass this here. So this is how we load the pre-trained weights. And then we set the detection transformer to evaluation mode or validation mode. Actually, not even validation mode, just eval mode for inferencing. Now we have to pass this URL from where we can download. I have the URL handy over here. This is the URL. I think that's it. This part is fairly straightforward. Torch has, okay, this should be hub. Okay, so this is the architecture now. You can see the full architecture getting printed, exactly the parameters. I mean, not the parameters, the exact architecture. Okay, so now we can write Coco classes and bounding box colors to be used. There are multiple ways to do this. We don't have to manually define it like this, but anyway, I have it manually defined here. I can simply copy paste the 91 Coco classes, and these are the colors or for the bounding box that we are going to use. So if we have maximum 100 bounding boxes, these 6 colors we will repeat. We will even for different classes. So maybe carrot and toaster may end up, if we have a carrot and toaster in our image, they may end up having the same bounding box color. Okay, so after this, we can now write a function function to scale the bounding box from 0 to 1 to image h comma w. So 0 to 1 will be because we use the sigmoid function, if you remember, the default bounding box size will be from 0 to 1 because that's how the bounding boxes are normalized. But we need to now, for plotting purpose, we need to put it back to h comma w scale so that when we are overlaying it on top of the image, the bounding box size is appropriate. I mean, it's corresponding to that of the input size. So first we have to define a transformation. So transform equal to t.compose. So t we had imported earlier in the import. Then first t.resize to 800. These are just done for we can use any parameter here. I think even if we don't resize, I don't see any problem. T dot 2 tensor. This 2 tensor is done because we want to convert the images from pillow format to tensor format. Then t dot normalize. In this normalization, we pass certain parameters, which are the mean and standard deviation of the data set, which is ImageNet data set that was used for pre-training the ResNet 50 model. So these numbers is already publicly known. If we don't know this, we won't be able to define it explicitly like this, okay? And I think I have an extra bracket, t.resize. Yeah, I think it's correct. Then define bounding box or box center x, center y, width and height from this format to xy format. xy format meaning the limits of x-axis left-hand side limit, y-axis left-hand side limit, I mean top limit, x-axis right limit, y-axis bottom limit. Define this, and then we say x center, comma y center, comma width, comma height. This is equal. This is already available to us from our x. So x dot unbind of 1, because the bounding box coordinates are already available from the output. This output will give us the bounding box. Actually, let me just remove this. This bounding box coordinate will give us the 4 of the outputs, which is at index 1. So we are just unbinding it so that we have these 4 items separately. Now we say b equal to, here we need to convert these coordinates into xy limits, left-hand side limit and right-hand side limit. So what will be the left-hand side limit? X center minus width by 2 multiplied by 0.5. That will be the left-hand side limit. Then right-hand side limit will be, or the y coordinate lower limit will be y center minus 0.5 multiplied by height. By the same logic, we can define the upper limits. This will be plus. From center, you add half width to reach the right-hand side limit. From center, you add half height to reach the top limit. Top limit or bottom limit, looking at based on the coordinate system. So this is now the bounding box coordinates converted into lower limit and upper limit format. Then we can simply convert this back into a tensor. So torch dot stack b along dimension 1. So here essentially what we are doing is we are converting. Here we had created an unbound set of x, y, w, h. Now we have a list of 4 items here. We are converting that into back into a tensor format. Values of b will be between 0 and 1. No, values of b will be between, it can be less than 1, right? Because the minimum value of c, let's say xc is 0. The maximum possible value of w is 1. So the minimum possible value of this guy will be 0 minus 0.5 multiplied by 1. So I think this will be between minus 0.5 and plus 0.5, if I'm not wrong, the values of these numbers. But that's okay because we are just using, this is not used for calculating any result. We are just using this to for plotting. So once we have this, we can scale this into width and height format. Then we say define rescale bounding boxes, B boxes. And we pass two things here, whatever is the output bounding box and whatever is the size of the image. And then we say image width and image height is equal to size. So width and height of the image we have, this is the actual width and height. Then B equal to, then we call this function of output box. So now we pass this output box into this so that now we get a tensor with bounding box, I think values between minus 0.5 and plus 0.5. Then we say B equal to B times torch dot tensor. Now we are scaling, and we are scaling such that image width and image height has to be used. So image width, first item will be scaled by image width because this is X coordinate. So image width. Second item will be scaled based on image height because second item is this Y coordinate thing. So image height. We have 4 items total. Third item will be scaled based on image width. Fourth item will be scaled on image height. So this is the X center left hand side coordinate. This is the this is the X left extreme, X right extreme, Y left bottom extreme, bottom or top. I have to check, but this is 2 extremes of Y scaled by the image height. This is 2 extremes of X scaled by the width. When I say extreme, extreme of what? Extreme of the bounding box, coordinates of the bounding box. Then that's it. And then return B. Just run this to see if everything is okay. Now we can predict the values of bounding box, predict outputs for a given image. So we are yet to pick the image of interest. So predict outputs, define detect, just writing a function for this. We pass the image, we pass the model, we pass the whatever transformation operations that we have defined. Then we say image equal to transform of image dot unsqueeze of 0 to add a batch dimension. Then outputs equal to model of image. And where have we defined the model? Model we have yet to define, or we have defined. Okay, we are yet to define the variable model, but finally this will be the model that we are using. But we'll define it in the next block. Outputs equal to model of image. And now once we have the output, we have to send the boxes. So which boxes? We just care about high probability boxes. So probabilities and the boxes to keep. In rescale B boxes, what is by, where is that? Oh, this was supposed to be B. My bad. I think it automatically, this was supposed to be return B. Thanks. Yeah. Yeah, I hope there is no other mistake automatically crept up, but things look good. Now probabilities are outputs of, so outputs is now storing 2 things, this and this, because these are the 2 things that are being returned from the detection transformer class. So outputs of, what was the first item? Predict logits. So this we take outputs of predict logits. Then logits need to be converted to probability. For that, we can use softmax. Then of 0 means we pick the specific, because we have only one image here. So batch size, we just, when we explicitly say batch index 0, we are picking one specific item. Then we need to have every single object query related item. So we have 100 object queries. So we are picking all of them. And corresponding to 100 object queries, we have probability predictions, right? probability for each object queried to be certain object. How many probability predictions do we have? Total probability prediction. So we have 100 boxes. Each of them can be probability predict. I mean, not that. I'm asking about probability. How many classes are there total to be predicted? We have 91 plus 2. 91 plus 1, 92 classes. 91 were the classes in Coco. Last one would be the no object class. So here, no object class, anyway, we don't have to draw anything. We are only drawing 91 rectangles. We are not drawing 92 rectangles maximum, right? So last item we don't need. So here we say pick everything except the last item. So softmax score, so output logits are converted to softmax. And then from that, we pick only the last, everything except the last object class. Because softmax will create a probability score distribution from with index from 0 to 90, 0 to 91. That will be 92 items. But you don't want the last item. Last item was the no object class, right? So you just eliminate it because no object you can't draw. Then you say you don't need all the boxes. You only need high probability boxes. So probas of or dot max of -1. So max of -1 means from the output logits corresponding to object classes, pick the maximum, the one with the maximum value. So let's say I have one rectangle and I have a softmax probability distribution, and with 80% probability, there is one particular class that is dominating. So I'm picking that, but then I have to check if the value of that is greater than some threshold. So I can say 0.6 or 0.7 or something like that. So what we are doing is first we collect all the probabilities except the probability corresponding to no object class. Then we say from the probability distribution, find the maximum probability value. And if that value is greater than 0.7, then I'm happy with drawing a bounding box. Otherwise, I don't want to draw a bounding box. So that is what is done here. And then we say, now we have to scale the bounding box, right? So B boxes underscore scaled equal to rescale. There was a function return, what was the name? Rescale boxes. Into the rescale boxes, we have to pass the output bounding box and the size of the image. So we pass outputs of predicted boxes, right? Pred boxes, I think. Yeah. Because output had two items, predicted logits and predicted boxes. So now logits is now correct. Now if we fix the logits, we only pick certain boxes for predicting. But now we have to pass the box 4 coordinates of those boxes to rescaling. So outputs of predicted boxes. But among those boxes also, I want to keep only, so batch dimension is 0, but I want to keep only boxes with this index. So this keep is basically the index of those boxes who are predicting a certain object with probability greater than 0.7. So these are now the indices that I want to pick. 0 because I'm again picking the batch dimension. So batch dimension was the 0th dimension, and I'm adding a value called 0, which means I'm looking at one specific item. And keep means I'm saying pass the prediction, the bounding box predictions only for those boxes whose confidence value is above the threshold of 0.7. Otherwise, don't even bother scaling the boxes because we are not going to plot it anyway. And second argument that we had to pass was image size, which is, where is image size? I don't have an image size. I'll have to define it, I think, or im.size. And then B box is scaled. Now in this function, this should return this from the probabilities. Only these indices I need to return. And whatever boxes we get after scaling, return all of them, because the scaling was done only for those boxes whose indices were this. So at the end of this function, it will return the probability distribution for boxes with probability greater than 0.7 and the scaled coordinates of those boxes. Okay, so this was actually not predict output. This was actually predict outputs and then scale the boxes. Keep only high confidence predictions. Okay. Now we are at the last part. Now we just need to upload an inference image. An inference. So here we mentioned the URL of whatever image we have to infer from. And then we say image equal to image.open. This is where the import request is being used. So request.get. Then we are getting from the URL, and stream equal to true. I don't know the importance of having this parameter. We can try without that. .raw. This is just happen to be the syntax. And then scores. So image URL we can define after everything else is working. Then scores comma boxes equal to simply this function detect. And into the detect, I have to pass image. I have to pass the detection transformer model. So model, although this variable we are not defined, we are only defining it here. We are passing the DETR. DETR is defined here. Here, DETR equal to DETR demo. So this is an object corresponding to the DETR demo class, and that is what we are passing here. And one more thing we have to pass, which is transform operation. So transform. This transform was defined earlier. And I can pick some random image. So let me just go to our website and pick something. And since we need only URL, I think it's a very easy thing. I can just right click, copy image address, and then paste it here in the URL, and that's done. And then plotting results. So this is the last part. Basically, we are done. We just need to run the whole code once. So define plot underscore results, then PIL image, whatever image we are passing, probability, and boxes. Size of tensors must match. Okay, let me check what's wrong with this. Dot unsqueeze of. Okay, this is unsqueeze of 1 because we are unsqueezing this dimension. That is one mistake. Okay, I'm not sure if there is any other mistake. I'll try running the whole code once. Okay, seems to be working. Let's move ahead. This is the last block and we are done. Define plot results and plt.figure. We can mention some figure size. Fig size equal to 16 by 10 or something. And then plt.imshow. And we are showing this image, PIL image, pillow image. Axis plt.get CA. Then now we have to plot certain boxes, meaning we have to display certain boxes over our input image. And how many such boxes are there? We have to do a loop. So for P, which is probability, now we are defining the X min, Y min, X max, Y max. And for this, comma C is the color of the box in zip of. Then we can define all of this inside here, probability, then boxes, boxes which are box coordinates, dot to list. So we are converting the tensor into list. Then we had defined colors somewhere. Where was this? this colors. So here we have only what, 1, 2, 3, 4, 5, 6 colors, but we may need more boxes, right? In the same image, we may have 10 boxes, 20 boxes. So we will need at least that many colors. So let's say colors multiplied by 100. So basically that 6 colors will repeat again and again 100 times. Then we say x.add patch plt.rectangle. So these are just syntax corresponding to plotting. We are plotting the rectangle such that x min, y min, then x max minus x min, this is the width, comma y max minus y min, height. Then fill equal to false. The bounding rectangle, we just need the boundary. We don't want to fill any color into the bounding rectangle. Color equal to this variable. So color is C, whatever color is being picked. So color equal to C, and line width of the bounding box equal to 1 or 2 or something. Let's keep it 3. Yeah. Then we say CL equal to p.argmax of p.argmax means whatever is the class name is p.argmax, and then text that we want to display will be like a dynamic text. So dynamic text is we want the class name. Class name we can pick from this. There are classes here. So the reason why we wrote the class names here is so that we can write it on top of the image. So this is classes of whichever is the argmax, the index corresponding to argmax, and the probability score also. So probability would be P of CL, and we just need 2 decimal points, 0.2 F. So floating point with 2 decimals, and text equal to that. So axis dot text equal to x min. So now we have to define where this text will display on the image. So x min, y min, text comma font size of the text. When we write the class, what should be the font size? Then b box equal to face color. So now this is not the b box. This is just the annotation of this text. So if the class name is, let's say, horse, then we just need to display it. So dict of face color equal to something, yellow or blue or orange. Then alpha, which is the transparency, we can set it to be 0.5, and that's it. Then plt.axis of plt.show, and then plot underscore results, which is this function itself, we are calling it. And for that, we need to pass image scores that is defined here, IM scores and boxes. Okay, I think with this, we are fully ready to execute the code entirely. Let's just run it once. Okay, of course, there is some mistake. It's not coming correctly. Some issue is there. Space is not allowed in string formatter. Space, which space? I think I have. Okay, something seems to be working, but not good enough, because I was earlier getting much better bounding boxes. So let me reduce this from 0.7 to 0.5. Let's see. Okay, clearly something is wrong. It's detecting wrong boxes. Let me do one thing. Let me run my other code to make sure if it is getting the same error or not. By the way, did anyone manage to get the code running? Or are you facing any issues? I'm sure somewhere I'm messing the way I'm picking the best boxes. Yeah, see here it is really good. Very high confidence scores, tie, person in the background, everything is getting detected, but we are not able to get that same thing here. Let me do one thing. Let me share this code with you and let me know if you are able to run this on some image. And once you are getting correct output, okay. Why don't you try this? Why don't you run the code with your own image, some image, and why don't you paste the image here in the chat with annotation? Just take a screenshot of the image and paste the annotated image here. We can also try Pexel's image or let's say animals. Okay, this is a nice cartoon image. Let's see how many copy image or copy image address. Okay. It's completely messed up. This panda is coming as elephant. This is horse. Bird is correct. It's detecting some pictures, but I guess that's because Coco dataset may not have pictures like this. Let's try for pictures that actually look like photos. Okay, how about this? Okay, this is working perfectly. So realistic images are working perfectly because Coco probably had that, but not cartoons, animals, photos. Okay, how about this? Okay, so here some things are working, but bounding box. Okay, I know one issue that might be there. There is a maximum limit for the image size that we can feed to this pre-trained model, 1600 or something. So I cannot feed very high resolution image. I have to pick a bit medium resolution. Maybe that's causing this bounding box issue. Let's see. Okay, this is a, yeah, this is a definitely a low resolution image. Yeah, so this one is working pretty well. So whatever objects Coco dataset had, they are getting. I don't think these deers will be part of the dataset. So please feel free to share the screenshots of whatever object detection classes you are getting. Here I will have to figure out where exactly is the mistake. Most of the things are correct, but I'm not quite certain where is the mistake, because the confidence score is a bit low. Also, wrong objects are being detected, but I think that will take time. So I have posted 2 assignments, I think 2 or 3 days back, on Swin transformer. This is based on the previous lecture. So one was about implementing the transformer for another data set apart from MNIST. Another one was counting the total number of trainable parameters to know the size of the Swin transformer that we have coded. So those are the 2 assignments. Detection transformer, I have not posted any assignment for the previous lecture because it was more about theory, but I will be posting one hands-on assignment based on today's lecture. So overall, what we have done in detection transformer is we understood the model, we coded everything except the loss calculation part, because we are not training the model, we are only inferencing from a pre-trained weights. But we understood fairly well all the different parts of the transformer itself. Only one thing which we did not do here is Hungarian loss. Even if we were implementing Hungarian loss, we would have used a PyTorch function. We would not have coded it from scratch. So you are not missing out too much there. So this brings us to an end of detection part. Now we are moving on to segmentation from next lecture onwards. So transformers, we have now looked at transformers for text, transformers for images, specifically for classification, transformer for detection, and now we'll move on to transformer for segmentation. So that's the plan. So okay, I think a couple of people are posting images after detection. Okay, nice. Okay, happy to see that the code is working. So try with different classes also, like not just people, objects, animals, everything. Just try that. But this is good. Happy to see the results. If anyone can figure out what's the issue in the earlier code, that'll be great if you can put it on the Discord. But otherwise, it's fine. I mean, we can figure out in 15 minutes. If I sit, I can figure out what's the issue. But right now, if I sit for it, it won't become like a lecture. So thank you so much. We can wind up here. We'll meet again next week. I'll post the assignment corresponding to this lecture on Monday. So please attempt that. I'll not keep a deadline. You can take your time. Thank you so much. See you next week. Have a good rest of the weekend. Bye.